Hey guys, in today's video we're going to check out the grade 12 chemistry paper 2 Gauteng Prelim 2025 paper. So let's jump right into the multiple choice questions. So 1.1 says, which of the following compounds has a formyl group as its functional group? So we have A, propan 1-ol, B, propanoic acid, C, prop-1-ene, and D, propanal. So as we can see here on this organic molecules sheet, we have our various different hydrocarbons, our haloalkanes, our esters, aldehydes, ketones, carboxylic acids, and alcohols. And all of these have their own different names, but a formyl specifically has to do with an aldehyde and a ketone, because these guys have carbonyl groups is the other word for it. So we have a carbonyl is this C with a double bond O over here, and this C with a double bond O over there. An aldehyde just has it on the end. That's why there's an attachment for an H over here, but a ketone is a C double bond O in the middle with a C on either side, so there's no space around the C to attach an H over there. So these guys have a carbonyl, and that means we're either looking for an ethanal or something with an L at the end, or a propanone or something ending in an one over there. So carbonyl is for both, but formyl specifically has to do with our propanal over here, because we have a propanal. It means we have a C double bond O over there, aldehyde ends with an Al over here, and we have meth, eth, prop. We have 4 C's in this chain, which means we just went straight for the answer. It isn't the propan 1-ol, that is an alcohol over here, like our alcohol over here, that ends in OH, and the type of functional group it would have is a hydroxyl for an alcohol. So that's why that one is out. And propanoic acid has a COOH over here, like we can see, and that is also not our functional group. And prop-1-ene is a hydrocarbon. It is a double bond over here, which means that that is also not the option that we're going with. So D over here earned us 2 marks. And then on to 1.2, the correct IUPAC name for the structure shown below is, so we have our various options over here. We have 1,4-dichloro, 4-ethyl, 3-methylpentane, 2,4-dichloro, 2-ethyl, 3-methylpentane. C is 3,6-dichloro, 3,4-dimethylhexane, and D is 1,4-dichloro, 3,4-dimethylhexane. So we have our various options here, and the first step we have to do when we identify an IUPAC name is to find our longest chain, where the most action is happening. By that, I'm talking about any functional groups, any double bonds, if there were anything like that, or any side chains, any CH3s like this. Generally, for numbering priority, we don't look at our halogens, our chlorines, or bromines, or anything like that, which means we just have to find our longest chain, okay? And sometimes this is a bent chain, which means we have 1, 2, 3, 4, 5, 6 over here, or we can count this way, 1, 2, 3, 4, 5. And 6 is a longer chain than 5, which means if we're going to go ahead and number it, we're going to write 1 here, 2 here, 3 here, 4 here, 5 here, and 6 here. So we just have to see if we're going to start from 1 here or from 1 here, because if we're going to count 1, 2, 3, we see we have this side chain over here on 3. And if we're going to count from here as 1, we're going to go 1, 2, 3. We're also going to see the side chain here on 3. So in this scenario, it doesn't actually matter whether we have 1 over here or 1 over here, as long as our longest chain is the bent chain over here, which means if we know our bent chain has 6 C's, 1, 2, 3, 4, 5, 6, which means we have meth, eth, prop, bute, pent, and then hex, which means these pentanes over here are out, and this is telling us that we also don't have an ethyl attachment group, which means, like we were looking here, an ethyl would be 2 C's stacked off the side chain, but as we established, we have the longest chain here, which is 6 C's, which means we are dealing with methyl attachment groups. We have this methyl over here, this methyl over here. These are our side chains, and then we just have to check the correct numbering between C and D as far as which numbers the chlorines get and which numbers the methyls get. So now that we're looking at the 2 options here, we have a 3,6-dichloro. So 1, 2, 3, there's a chlorine. 4, 5, 6, there's a chlorine. So there's a chlorine and there's a chlorine, which means we have a 3 and a 6 as we've done our numbering here. And then we have 3, 4, 1, 2, 3. We have 3 over here and then 4 over here, dimethylhexane. And that's looking good. We just need to check D because C is not the correct answer, because what we have for D is 1, 4. So it means we actually had to change our numbering 1, 2, 3, 4, 5, and 6, because what's happening is that because the side chains are in the exact same positions both ways, the most action is taking place here with the Cl on 1 instead of having the Cl happen on 6. So it's always about where the most action is happening. By that, any side chains, any attachment groups, or any double bonds, or anything like that. That's where we start the numbering priority, which means if we're going to look at D now with this changed numbering, we're going to see that 1, 4, so we have 1 and 4 dichloro, meaning 2 chlorines, perfect. Then we got 1, 2, 3, we have a 3, and then a 4 is this CH3 over here. 3, 4 dimethyl, meaning 2 methyl attachment groups, hexane. 1, 2, 3, 4, 5, 6. And that means D is our final answer, just because the most action is happening by this chain over here. The numbering of the Cl attachment group needs to be on the 1 and not the 6, which means C is out and D is our final answer for 2 marks. And then 1.3 says, consider the following reaction. So we have step 1, we have a CH3, CH3 plus HBr, and that goes to compound P, and then compound P is taken in step 2, compound P plus NaOH goes to compound X plus NaBr. So they want the IUPAC name for compound X, and we have a couple of options here. We have A is butan 2-ol, B but2-ene, C 2-bromobutene, and D 2-bromobutane. The easiest way to work through this one is to do our reactions, because for step 1 we have our CH3, so we have a C, a C, a C, and a C, and we have 3 H's around the first one over there, and then we have 1 H on here and 1 H on here, and then we have 3 H's around this one. So we have 1, 2, 3 over there. And these middle two guys aren't quite right, because we have 1, 2, 3, and there always need to be 4 lines around each thing. And we can't draw the H over here because they didn't have an H over there, which means the only way to satisfy this middle portion here is to draw a double bond in between it, which means we have this meth eth prop but, this but2-ene, and we have to add HBr is what they told us, which means we're going to draw this down here, forming compound P. This is some sort of addition reaction, because an addition reaction is when we are adding something to a double bond and the double bond breaks. Because if we have our meth eth prop but, and we had these 3 here, we had this one here, and these 3 over here. If this bond over here breaks, what's going to happen is we're going to form availability over there and over there for this HBr to attach to, which means we have a Br over here and an H here. In certain scenarios, we'll have to work with Zakhovnikov's rule as to which one gets the Br and which one gets the H, but we'll deal with that when we come to a later question. But right now, because Br will either be on the 2 here or the 2 here, it doesn't really matter, which means addition is going from 2 to 1, and it's always a double bond breaking, forming a single bond, so we can attach this hydrohalogen in this case, which means compound P we now know, which is great. So this is P for us, and then they're taking P and they're adding NaOH. So we are taking this guy over here and we're adding NaOH plus NaOH. And now we may be asking ourselves, is this an addition reaction, an elimination reaction? What's happening? Because we're seeing our compound P here, a hydrohalogen with single bonds, and we have NaOH. This is a hydrolysis reaction. This is something we'll have to learn from our sheet. But what's happening is that we have 2 reactants over here and they go to 2 products over there. And as we can see, this OH and this Br, they swap. So this Br over here swaps with this OH and we form 2 new products, which means we aren't breaking any double bonds because there aren't any. So it's not addition. We also aren't forming any double bonds, because if we were to look at this reaction above and we reversed it, that would be an elimination reaction, because we are removing HBr. It's going this way. We have removed the HBr and then we're forming a double bond. Which means that if we know that it's not addition and it's not elimination, it is some sort of substitution reaction. Like we established here, we're swapping the OH and the Br. We're going to have our H's around here, and where the Br used to live, we're going to have the OH that is going to join here. Because we're not breaking any double bonds or forming any double bonds, we're just swapping the OH and the Br through hydrolysis, which means that this will be compound X, and as we established, our Na will be here and the Br will join it. So we have NaBr over there, which means this was step 2, and we're now dealing with a meth eth prop but, some sort of but over here, as they all are. We have a OH on our hydrocarbon, which means that we have some sort of alcohol now, as this is our hydroxyl group. which means as we can see here, it is on our 2, whether we were counting this way or this way, whether our BR was here or over there, our OH would be on the 2. And as we can see here, A is butan, meth, eth, pro, but, butan, 2, ol. Ol indicating alcohol, which means that A is our final answer here. Butene, this isn't a double bond. This also doesn't have a bromine attached to it like C, or a bromine attached to it like D. As we substituted that, the BR with the OH over there, which means that A is our final answer for 2 marks. And then 1.4 over here says consider the organic compound propanol. Okay, so we were discussing propanol in 1.1 over here. That was an aldehyde, which means we are now dealing with the aldehyde here again. It's always nice to just look around in the paper to see if there are common patterns or questions that we've touched on earlier come up later as well. So it's saying which of the following is correct for the homologous series and the intermolecular forces between the molecules of the compound propanol. So just like we were looking at earlier, the organic molecules sheet that we have over here, we have our aldehyde, our propanol, as you can see, aldehyde here, the Al over there, and then we have an L over here, our ethanol in this scenario on this picture. But propanol is meth, eth, prop, so we have 3 C's instead of 2 C's. That's the only difference. But as mentioned in question 1, we know that this is an aldehyde over here, propanol, just like it is here, and it is not a ketone. So B and D are out because a ketone has an -one over here, ONE, as the suffix for the name. Okay, which means B and D are out. And as we can see here, that means we are dealing with the homologous series, which we've identified, and then the intermolecular forces, which we have to determine whether it's a hydrogen bonding or just dipole-dipole forces. And as we can see here on the sheet at the bottom, we have intermolecular forces here, and aldehydes have London forces and dipole-dipole forces. They do not have hydrogen bonding. That is only for carboxylic acids because the H is directly attached to the O, and alcohols because the H is directly attached to the O. But aldehydes have dipole-dipole forces because the O and the H are not directly attached to each other, but the C double bond O, regardless of the double bond, is here, and the electronegativity difference between C and O is in the range of dipole-dipole, which means that C will be our answer as it is an aldehyde, propanol, and it has dipole-dipole forces like we can see over here. So that just earned us 2 marks over there. And then 1.5, we're just going to work through this one quickly because on the memo it says accept all answers because it was phrased a bit weirdly. So what we're going to see here is 1.5. The graphs below illustrate the distribution of the same amount of 4 different O2 gas samples. So it's gas in every single graph over here, which means each sample is at different temperatures. And then it's saying which gas is at the highest temperature. So B and D are not our usual forms because this is usually relating to Maxwell-Boltzmann, which is a part of our rate of reaction section. So B and D are generally going to be out because what we have is something that peaks and then it starts to get lower as the temperature increases. So as we move more to the right for the temperature, it peaks at some stage and then it goes down. So C can also be true because C will also peak and then it will start to go down, hence the distribution curve. So right now, this guy starting at the origin is fine, but after it crosses the activation energy, it doesn't start to decrease again, which means it isn't following our normal Maxwell-Boltzmann trend. And then D also doesn't work because we aren't starting from the origin, which means at 0 degrees Celsius, the number of molecules is the most and then it's decreasing, which isn't following the trend. So we're just going to compare A and C just so we can understand Maxwell-Boltzmann in this question, but either way, we could just pick any answer. So they're saying which gas is at the highest temperature. So Maxwell-Boltzmann is usually about where the temperature is highest here. So as we move along our x-axis, say now we're starting at 0, and then here we're at 10, and somewhere in between we have 5. And here as well, we have 0, and then 5, and then 10 over there. As we can see, there'll be a higher temperature at this highest peak over here, and over here for A is a lower temperature at this peak over here, which means that C will ultimately have the higher temperature because we have more molecules as we move up this way that are at a higher temperature overall compared to here for A. So C would be our answer, and this is generally what happens when we have some sort of temperature change for Maxwell-Boltzmann. It'll shift the peak more to the right and then will look less steep. It's not about how steep it is, it's about how far to the right it is in terms of temperature over here, which means these molecules, a nice way I like to describe it to some of my students, is that they're all cold, they're all shivering, they're sitting by this y-axis because we have all these molecules that don't have a very high temperature, which means the peak happens earlier, and as we turn from reactants to products in a reaction, we have less molecules with sufficient energy to overcome the activation energy, which means we're going to get less reactants to products over there. But in this scenario, we have a higher peak here, where we have more molecules that are not cold and shivering by the y-axis, and they have a higher energy at their peak. So when we start to convert from reactants to products, we ultimately have more reactants that have enough energy greater than the activation energy to convert to products. That's what this dotted line represents, the activation energy. But this question specifically is too broad, and they needed to refine the question. But if we're just going to look at A and C, C has a higher temperature. It has been shifted to the right with more molecules having a higher temperature. So we're just going to use C as our answer here. And in this scenario, that would earn us 2 marks. Question 1.6 says, consider the chemical reaction shown below. We're now dealing with some chemical equilibrium question. So we have 2NO plus O2 goes to 2NO-O2. And this is a forward and reverse reaction, so it's chemical equilibrium. And here, delta H, we're dealing with some sort of reaction. So we have two different graphs over here. We have a graph like this and a graph like this based off of grade 11 work. And what's happening is that this y-axis is our EP over here, our potential energy. If we're going to put values here, let's call this 10 and this 5 over there, and then 10 and 5, in line with the two different lines here, because we always have our reactants, and our products, and same thing here. So the equation that we're dealing with when we're looking at here, just to understand what the negative means, is that we have to go E of products minus E of reactants. As soon as we do that, we're going to see what type of graph we're dealing with, because this first graph here is where we are losing energy. It is exothermic. So we have an exothermic graph because our products have less energy than our reactants, okay? And this graph over here, where our products have more energy than our reactants, is an endothermic graph, which means we can take E prod minus E reactants here for our endothermic graph, and that means we have 10 minus 5, and we have 5 kilojoules over there. And it's a positive 5, which means endothermic reactions always have a positive value. But if we're looking at an exothermic reaction, we take E prod, which is 5, minus E react, which is 10 over here, and 5 minus 10 is negative 5. So we are losing energy. We're always going to have a negative value over here. That being said, we have a negative kilojoules over here for our enthalpy. This is what this all represents. And that means we are losing heat. And the way that we would place losing heat for a chemical equilibrium reaction is to go plus heat over here. Because we are losing heat, heat will be a byproduct, something that is released in this reaction, and it is sitting on the product side over here with our 2NO2. So we have them all grouped together. This is in one beaker, but the heat, there's more heat being released on our product side. Okay, so that's just something to keep in mind as we jump in, because it's saying a change was applied to the equilibrium of the gas mixture. The mixture returned to equilibrium and a second change was applied. The following graph shows the effects of the two changes. So here we have concentration in moles on our y-axis, and we have time on the x-axis with a temperature change here and a concentration change here. So they've marked off what type of change they've made, and that's pretty helpful for us. So then it says, identify the applied changes that best account for the shape of the graph. So they've also told us NO is over here, O2 over here, and NO2 over there. So if we're going to look at the temperature change here, we're going to then see what we're working with. Because for chemical equilibrium, what we're trying to do is we're trying to see how we can move the forward and reverse reaction based on the changes we can make. So a temperature change specifically, if we know that heat is over here and we increase heat in the system, it will favor the reverse reaction, because what happens is heat is living on this side. It means if we're increasing it, we're pushing up this seesaw. Over here, there's a ball on the seesaw, and the ball is going to roll downhill in the opposite way so that ultimately the seesaw can balance again. So if heat were to increase, it would favor the reverse reaction. 2NO2 would decrease, and 2NO and O2 would increase. So we're just trying to see if that is happening over here, because what's happening is that NO2 is decreasing, okay, and O2 and NO are increasing, which means that we have an exothermic reaction. Heat is living on the product side, And if we have increased heat, NO2 is going to be used up. It's going to break down because it's all in the same beaker here. It's going to break down and it's going to form O2 and 2NO. So it's going to go this way. We're going to form these reactants again. And that is what's happening as O2 is increasing, NO is increasing, and NO2 is decreasing, which means we have increased heat in the system, which means A is out and B is out. Because the temperature change, decreased, those don't fit, as we can see based on the temperature change over here, which means C and D, we just have to see whether O2 was increased or the NO decreased for the concentration change over here. Because what we're seeing is a sharp drop of NO, and that is a good indicator that it has been removed from the system, and then we're going to see how the system has to counteract that disturbance, which means NO decreased. We do have the option over here for D, and therefore D is our final answer. Because as soon as NO decreases, it means that it is going to once again be the seesaw analogy. We've just pulled down the seesaw this time, and therefore the ball on the seesaw is going to roll downhill, favoring the reverse reaction, which means if we're going to look a bit further, NO was decreased to NO2. It is decreasing further because we are favoring the reverse reaction. So it is being used up as it forms more O2. O2 over here increased because the NO decreased. And then 2NO, even though we removed it from the system, this 2NO2 is breaking down to form the O2, and then 2NO again until it reaches equilibrium. So we've removed it, a sharp drop, and then it starts to increase as we favor the reverse reaction, which means D is our answer, C is out, O2 did not increase. That isn't what sparked this concentration change, even though O2 did increase from what we can see, but that isn't the change that we made. So D is our final answer for 2 marks. And then 1.7 here says, which of the following statements about water is true? So 1, it is a weak electrolyte that undergoes autoionization. And then 2, the equilibrium constant for the ionization of water at room temperature is 1 times 10 to the negative 14. 3 says it ionizes completely at room temperature, hence H3O plus equals OH minus. 4, the ionization of water produces twice as many hydronium ions as compared to hydroxide ions. So A, B, C, and D have different combinations of which ones are correct. D has all of them, and then the others only have 2, and we have to see which ones are true. So what happens with water is that it is H2O, as we know, and it breaks down by itself, forming H3O pluses and OH minuses, but not very strong. They don't just conduct by themselves like acids and bases, which is what this section is based on. So H2O liquid breaks down into H3O plus OH minus. But what we have to do now is balance this equation because we have H3O, OH, so we have 4 H's here and 2 O's here. So here we have 2 H's and 1 O, which means we have to go ahead and write 2H2O so that this is balanced. Because then we have 4 H's, 1, 2, 3, 4 H's there, 1, 2 O's here, and 2 O's over there. So 1 is true. Water is in fact a weak electrolyte that undergoes autoionization. This just means that it breaks down by itself, forming these guys, and then it goes back together to form water. But this ionization is only partial. That's why it's a weak electrolyte. It doesn't ionize completely. And that's why 3 is not true, because it ionizes completely at room temperature, means that it breaks up completely, which is not true, which means they don't ionize completely. And it being a weak electrolyte means it is only partial and it does not ionize completely. So then if we're going to look at 2 over here, this number 1 times 10 to the negative 14 might look familiar to us because we have 1 times 10 to the negative 14 here. This is our kW value. So it's saying at 298 degrees Kelvin, 273 degrees Kelvin equals 0 degrees Celsius, but 298 degrees Kelvin is 25 degrees Celsius. So we're just adding 25 to 273 and we have 298, and that's how we convert Kelvin to Celsius. But what this is saying is the equilibrium constant, the kW constant, for the ionization of water at room temperature, 25 degrees Celsius being room temperature, is 1 times 10 to the negative 14. And that is true over here as we've been given this constant on our formula sheet. Okay, which means that 1 is true and so is 2, and then we just have to see if 4 is true or why it isn't. Because the ionization of water produces twice as many hydronium ions as compared to hydroxide ions. So that isn't true, as after we have balanced this equation, we can see that there's a 1 in front of our H3O plus and a 1 in front of our OH, which means that there are not twice as many hydronium ions, compared to OH minus ions. They are exactly the same amount in terms of moles, and that's why 4 is out and 1 and 2 is our option, and that leaves us with the answer A over here. As water is a weak electrolyte that undergoes autoionization, breaking down a little bit and then reforming water, and the equilibrium constant at room temperature is 1 times 10 to the negative 14, as we could see on our formula sheet. So A is our final answer here for 2 marks. And then 1.8 says, a lab assistant prepares solutions of nitrous acid, so nitrous acid over here, and hydrogen cyanide acid over here, both at the same concentration. So the Ka value, the coefficient of how acidic a solution is, are given as follows. We have 4,6 times 10 to the negative 4, and we have 6,17 times 10 to the negative 10. So 10 to the negative 10 is a lot smaller than 10 to the negative 4. Regardless of the numbers in front, we are looking at the scientific notation to figure out how small the value is compared to how big the value is. So the bigger the value, the more acidic a solution will be, okay? And the smaller, the less acidic, which means this is more acidic because it's 10 to the negative 4, and 10 to the negative 10 is a lot smaller. So which of these two acids is the stronger acid and which has the higher pH? So the stronger acid, as we established, is the nitrous oxide, the HNO2 over here, which means C is out and D is out. And then the higher pH is on a scale of 1 to 14. 7 over here is neutral, and the lower the number, the more acidic it is. The higher the number, the more basic it is, or the less acidic it is, okay? Which means that if something is a stronger acid, like our nitrous acid, it will be closer to 1 over here. But if it's a weaker acid, it will be closer to 7, or just not as low down to 1. Which means that a higher pH is when something is less acidic. As we move from left to right, we get more and more basic. So we have two options here. We know HNO2 is our stronger acid, but the higher pH will be the weaker acid, which means the higher pH will be HCN, because nitrous acid will be over here, but hydrogen cyanide acid might be over here with a higher pH. So therefore B is our final answer for 2 marks. And then 1.9 says, calcium metal reacts quickly with hot water to produce calcium hydroxide and hydrogen. We have calcium metal and water forming calcium hydroxide and hydrogen. So identify the oxidizing and reducing agents in this reaction. So this is redox. We're dealing with oil rig. Oxidation is loss of electrons and reduction is the gain of electrons, which means if we are gaining an electron, we are becoming more negatively charged, because we have more negative electrons compared to the protons that it currently has. Oxidation is loss of electrons, means it becomes positively charged, as we are losing the negatively charged things. Therefore, we are more positive because we've lost some electrons. We'll talk about the agents just now, but if we're going to go through our grade 11 process, how we'd normally do it, any lone metals or any lone elements have a charge of 0 because they are balanced in terms of protons and electrons. So that means we can look at CaOH2 over here, which means there's two ways to try and get the charge of Ca. We can always unwrap the numbers because the 2 came from the Ca over here and the OH had a charge of -1 over here. So we can always unwrap them. This is how we did it in grade 11. We would combine things by taking the charges on the periodic table, and then the charge of the Ca would go to the OH, and then the charge of the OH would go to the Ca. And not in terms of positive and negative, but in terms of the numbers that they have, which means we end up having Ca1, OH in brackets 2. So that means we have a charge of +2 here for our Ca, or if we prefer, we can go to our periodic table and we can write +1 over here and +2 over here, +3, plus -4, -3, -2, and -1. This has to do with the valence charge when it comes to bonding different elements, and as we can see here, we have our Ca, which has a charge of +2, which is exactly what we figured out by unwrapping it. But if you prefer this method, you can always come to your periodic table and then figure that out. It might just be a little bit complicated with transitionary metals, and that's where we would have to unwrap it, unless they specifically told us whether it had a charge of 2 or 3, depending on how it's bonded. But that means Ca has a charge of 2. And if we're going from Ca with a charge of 0 to Ca with a charge of +2, once again, we're not looking at the OH2 over here. This is just spectating, and redox has to do with how the electrons move for the metals for the most part, which means if oxidation is the loss of electrons, something is becoming positive. So we're going from 0 to positive 2 here. And this would be our oil, our oxidation portion over here. And then that means our H2 going to H2 over here is going from, if we're going to do the same thing, H2O, H has a charge of 1 from our periodic table, or we can just swap the numbers over here, which means H had a positive 1 that we are taking from here, and O has a charge of -2 that we could also get from the periodic table, which means H had a +1 over here, and then a lone element over here has 0. It's going from positive to less positive, so it is gaining an electron to get less positive, okay? So it's becoming more negative, which means this is our Rig portion. As soon as we figure out which is our oxidation half reaction, it means the other one is the reduction half reaction. But now, coming to the questions, it says identify the oxidizing and reducing agents in this reaction. And one thing to keep in mind is that oxidizing agent and reducing agent is a bit backwards. So first off, agent means the thing that is doing the thing, which means like 007, it is taking the action, and it is always on our reactant side. It is never on the product side, which means if there was anything on the product side here, we would ignore that and that option would be out. But then the oxidizing agent meaning the thing on the left, one of our reactants, oxidizing means it is the thing that undergoes reduction. So that part is backwards, which we'll always have to note. So oxidizing agent means it is the thing that undergoes reduction, which means reducing agent is also backwards. Reducing agent is the thing that undergoes oxidation. Agent, the thing on the left side in our reactants, which means the oxidizing agent is the thing that undergoes reduction, and that is our water over here, because the agent is on the left side, it is not the H2. That means water as our oxidizing agent is true, which means we have an A and a C as an option, which means D and B are out. But then if we're going to look at reducing agent is the thing that undergoes oxidation. That is our Ca going to CaOH. And then agent is just the thing on the left side. It is our reactant, which means that Ca is the option that we need for our reducing agent. And that is why C is our answer over here for 2 marks, and A is not our answer because it is saying that H2 is the reducing agent. So therefore, A is out. And then last question here, 1.10 says, the following half reactions show some predicted standard reduction potentials for the oxides of a hypothetical element X. So we have 2XO3 solid plus 2H plus 2E minus goes to X2O5 solid plus H2O liquid. So these next ones are quite similar as far as the H's over here, just with different balanced numbers, the electrons breaking off and then forming water. On the right side, we have some sort of variation of X, and the left side, we also have some sort of variation of X bonded with O. So what they're asking for here is the strongest reducing agent, and we have to see whether it is XO3, X2O5, XO2, or the X3+. So just like last time, a little bit backwards, just because we have a reducing agent over here. Just like the previous question, reducing agent was backwards because what we know is that the reducing agent is the thing that undergoes oxidation. And oxidation is the loss of electrons. So right now we're seeing two-way arrows over here. And if we're going to lose electrons, are we going to be going this way? Or are we going to be going in the reverse reaction? And the correct answer would be going in the reverse reaction, because as we're here, we are breaking apart and losing electrons, and therefore electrons are floating around as one of our reactants, or in this case, the product, because it's the reverse reaction. So that's what we're looking at first, which means we've correctly identified that, and that is great. And that means the agent portion has to be the thing on that side that is doing it, which means it's either X2O5, which is an option, 2XO2, so we have an option over here for XO2, or X3+. Okay, so those would be the options we're looking at because we know which direction we're going because we are undergoing oxidation. Reducing agent means we are losing electrons, and the electrons on the side. One thing to keep in mind with table 4b, we're always using table 4b for galvanic or electrolytic cells, is that as we move down the table, we are increasing oxidizing ability. And what we notice here is that as we move down and down and down, we have positive values that get more positive in terms of the potential voltage that the cell has. As we move up, it becomes more negative, which means something increasing in oxidizing ability. Remember, that's backwards. Increasing oxidizing ability is the reducing agent. So as we go down, we are talking about the reducing agent over here, and it has a bigger positive charge. But one thing to keep in mind in this question specifically is that we now know which direction we're going in. We have to look at these voltages over here. And these electrovoltages here have to do with the forward reaction, which means as soon as we're going into the reverse reaction, we are going to change the signs of all of them. Not the values, but just the signs, because it was negative 1,34 this way, which means it'll be positive 1,34 that way. So we have a positive 1,34 here. Over here was a positive 0,11. It becomes negative for the reverse reaction. And then here again, negative 0,46 becomes positive 0,46, which means that we've identified that we need the biggest positive value. We realize that we're going in the reverse reaction because oxidation is loss. We are losing electrons and they are breaking off. And that is because the strongest reducing agent is the thing that undergoes oxidation, which means now all we have to interpret is just which of these values with the changed signs has the biggest number. And as we can see, positive 1,34 is the biggest value, which corresponds with the increasing oxidizing ability over here. As we move down, it has a bigger positive value, which means that the agent is the thing on this side, and the thing on the right of the arrows with the most positive value over here is our X3+. It is the metal over here because X3+ is the reducing agent, the thing that undergoes oxidation, which has the highest electrochemical voltage based on the reverse reaction being positive and not negative. And that is why D is our final answer over there. So this is quite an involved question. Let me know if there are any questions on this one in the comments below or any other questions as well. But that earned us 2 marks over there and 20 marks for this whole section. Question 2, it says the letters A to F in the table below represent 6 organic compounds. We have the structural formula here for A with a double bond O over there. We have our condensed molecular formula over here with just C's and H's, so some sort of hydrocarbon chain. Here we have a bromine and a chlorine attached, so some sort of hydrohalogen for C. For D, we see our Cu over here, so this is some sort of carboxylic acid. And then E, we have ethine. This is a triple bond for a hydrocarbon. And then as we can see here, we have an OH for F. This is some sort of alcohol with our hydroxyl group over there. So 2.1 says, name the homologous series to which each of the following compounds belong. We just ran through them quickly, but 2.1.1, A is a C double bond O over there, which means we have this sheet over here, this organic molecule sheet, and we're going to reference it as we work through it. It just helps us so you guys can visualize it a bit more clearly. So what we have here for A is the double bond O on the C. So if we're going to look here between the aldehydes and the ketones, we can see that we have a C double bond O over here and a C double bond O over here. But there's one difference because the aldehyde has this H attached to it over here. So a little memory device is CHO. Aldehyde is such a weird word. It's just a way to remember that compared to ketones, which only has a C double bond O over there. And what we can see is that this C double bond O for a ketone has 2 C's on either side and no place for an H to be attached to it because there are already 4 lines around the C. And if we're looking here, we can see that there are 2 C's around it. C double bond O, there's no room for an H because it's not on the end, which means it is not an aldehyde. And there are 4 lines around it. So we just have a ketone over here because of our C double bond O. That means we can just go ahead for 2.1.1. We can write ketone and that would earn us 1 mark over there. And then 2.1.2 for C, we can see that C here has bromines and chlorines on it. So like we mentioned just now, something with a bromine, a chlorine, and an iodine is a haloalkane. So a haloalkane is a hydrohalogen, but a haloalkane is when we have the halogen attached to an alkane chain. So we can just go ahead and write haloalkane and we will get our 1 mark over there. And just as we mentioned, ethine is our triple bond over here. As we can see, we also have our Cu over here for our D, which is a COOH, which is always on the end here for a carboxylic acid. And then an OH over here is our alcohol that's attached over there, like our ethanol in this example, as we can see on the sheet here. So that earned us 1 mark. And then 2.2 says, write down the IUPAC name of compound C. Okay. So we have compound C over here. I'm going to redraw it for us. So wherever I've just drawn lines, that means they're just the hydrogens over there. In the test, we have to draw all the hydrogens, but for now, I'm just going to leave them like that. But what is important for the naming convention specifically are the location of the bromine and the chlorine, as well as which one is our longest chain. Because our longest chain over here is a bent chain. And if we're going to count it this way, we can go 1, 2, 3, 4, 5, or we can count 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Doesn't really matter how we bend the chain, as long as we can see that it's 5 C's either way. But what is important is where we start the numbering from. because the general rule of thumb is always start the numbering where the most action is occurring. By that, there's a bromine attached on this first C here. We have to number this C as 1 compared to numbering this C as 1. Because if we number this C as 1, then bromine will be on 5, and we don't want that. It's always about where the most action is occurring. So therefore we have 1, 2, 3, 4, and let's call it 5 over here, how we bend the chain. So this means we have to write the halogens first and in alphabetical order. So that works out for us because what we have is 1 bromo, 3 chloro, and then we see that this C over here didn't have a number because it's not on our main chain, which means that it is a methyl attachment group. And that means we have 4 because it's attached on the 4 methyl. So we've dealt with the bromine, the chlorine, and the methyl over here, which means all the side chains are dealt with. And then we just have to say our longest chain, which is meth, eth, prop, but, pent, and they are all single bonds. So we have pentane, which means this is the IUPAC name of compound C, and that would earn us 3 marks. Because then 2.3 says write down the letter for the compound that has a carbonyl group. Okay, so what we're looking for is a carbonyl group is from a ketone. It is when we have a C double bond O over here. In some papers I've seen them call an aldehyde a carbonyl, but usually it's called a formyl. A way to remember that is that there's a substance called formaldehyde, and that substance has the name aldehyde in it, so it's basically formyl plus aldehyde, and we have formaldehyde. So formyls are from aldehydes, ketones have carbonyls. These are all the names for the functional groups. Okay, carboxylic acids have carboxyls. So you might be seeing a pattern right now as far as the naming. Alcohols is a little bit different. They are called hydroxyls. So we still have the hydroxyl. And those are the general functional group names that they ask for based on aldehydes, ketones, carboxylic acids, and alcohols. So that means write down the letter that has a carbonyl group. As we established, a carbonyl is from a ketone. A ketone is what we labeled A. So therefore, write down the letter. We're just going to write A over here, and that'll be 1 mark over there. So then 2.4 says write down the structural formula for the 2.4.1 functional isomer of compound A. So functional isomer, isomers have the same amount of C's and H's, but functional means that it will have a different lock and key. Just like this sheet we were looking at, having a different functional group places us in a different category over here, a different homologous series. So the most common functional isomers have to do with esters and carboxylic acids. So these ones are very common. And then aldehydes and ketones. These guys are also very common because we just have to move the double bond O to a different location. And then we have changed the homologous series to which it belongs, which means we have esters and carboxylic acids, aldehydes, and ketones. So considering these are the 2 options we have as far as functional isomers, same amount of C's and H's, as we can see A over here, and we established it is a ketone, which means if we're going to draw it, all we have to do is move this double bond O to the end. As we can see here, we have propanone in this example here with a double bond O in the middle. And then the only difference is moving the double bond O to the end. So that means we have C with 3 H's around it, a C with 2 H's around it, a C again with 2 H's around it, and then we have our C with our double bond O on the end. And then we have 1, 2, 3, and we need a 4th line. So therefore we put the H over here. And it doesn't matter whether we put it on this side or on this side, as long as it's on the end, that's where we'll start counting. So therefore it's always on the 1, because it'll be 1, 2, 3, 4. Or if it was on this side, it would be 1, 2, 3, 4. And that is the functional isomer of the ketone. This will be meth, eth, prop, but, butanol. And that is the IUPAC name for the aldehyde. So that just earned us 2 marks over there. And then 2.4.2 says write down the structural formula for the ester with the same molecular formula as compound D. And just like we've done previously, aldehydes and ketones are 1 pair of functional isomers. And here we're talking about an ester with the same molecular formula as compound D. Compound D is a carboxylic acid, and we have to turn it into an ester. So this is just another way of saying draw the functional isomer for D, therefore making this carboxylic acid an ester. And as we can see here, we need the same amount of C's and H's, but in a different arrangement. So if we have a methanoic acid, we have 2 C's. We could then have a methyl methanoate, for example. So say now this guy vanished. We would then have to rearrange these 2 C's in the format of having an oxygen bridge, just like our ester over here, where we have a COO or cocoa is a good memory device for an ester because Coco Chanel smells good and esters generally smell good. They are in the perfumes. So we turn it from that compared to a COOH. This is our carboxylic acid. So all we have to do is change the arrangement of the C's and H's so that it no longer has the COOH on the end, but it has a COO in the middle. Okay, and as we can see here, we have 2 C's. That means we're going to have 1 C, an oxygen bridge here, and then another C over here. And then on the one side, we have our 3 H's, and then on this side, we have our double bond O, and then we have 1, 2, 3. We need a 4th line, so we're going to have to draw an H over here. And this would be the correct formatting here. This was methanoic acid, and now what we have is splitting up our oxygen bridge. We have a methyl methanoate. So the O8, the methanoate or the ethanoate or any sort of O8 is the side that has the double bond O on it. And this would earn us 2 marks because this is the ester with the same molecular formula as compound D. It is the functional isomer of compound D. So then 2.4.3, the tertiary alcohol of compound F. So we have primary, secondary, and tertiary alcohols. And we can first see that this alcohol here, this hydroxyl, is attached to a C that is attached to 2 other C's, which means that in a scenario like this, if this whole side was gone, this would be a primary alcohol because there's only 1 C attached to the C that the hydroxyl group is attached to. So it's not about it being attached on the first or the second C, it's about how many C's are attached to the C that the hydroxyl group is attached to, which means that in this scenario, we're currently dealing with a secondary alcohol because there are 2 C's attached to the C that the hydroxyl group is attached to. And that means if we're turning this whole molecule into a tertiary alcohol, the only way we can do that is by adding a C over here, because then there'll be 3 C's attached to the C that the hydroxyl group is attached to. And we don't want to add additional C's. It means that we're going to remove this guy and we're going to shift it over here so that we have this arrangement with 3 C's attached to the C that the hydroxyl group is attached to. So therefore, I'm just going to go ahead and draw that quickly. And this would earn us 2 marks over there because we have 3 C's attached to the C that the hydroxyl group is attached to, and we haven't added any more C's or taken any other C's away, and therefore kept the same amount of C's and H's. So that just earned us 2 marks over there. And then 2.5 says, explain why compound A is not an unsaturated hydrocarbon. So compound A over here is not an unsaturated hydrocarbon. So I have a memory device for this. I say I sat down to sing. So what this means is that saturated bonds are single. So I sat down to sing is the memory device, which means saturated bonds are hydrocarbons with only C's and H's that only have single bonds. And then unsaturated are any hydrocarbons with double or triple bonds in the hydrocarbon chain as well. 2 marks here, which means there's 2 parts that we have to refer to. First, we don't see any double bonds or multiple bonds between any of the carbon atoms, any of the C atoms in our hydrocarbon chain. So we can write unsaturated means multiple bonds between 2 C atoms. So that will earn us 1 mark over there. And we can see that there are no double bonds or triple bonds between the C's specifically. That mentioned the unsaturated portion, but the hydrocarbon portion, hydrocarbons only have C's and H's. This has an O attached to the C, and therefore it cannot be a hydrocarbon either. So we can also write there is an oxygen atom, and hydrocarbons only have C's and H's. So this explanation would earn us 2 marks dealing with the unsaturated portion and the hydrocarbon portion, because there are no double or triple bonds between the C's, and there should only be carbon and hydrogen atoms, and we have an oxygen atom attached to the C. Cool. And that just earned us 2 marks over there. And then 2.6 says, which letter in the table above represents 2.6.1, an unsaturated hydrocarbon? So this is a nice follow-on question because we just chatted about an unsaturated hydrocarbon, which means we can only have C's and H's and we need double or triple bonds between the carbons. So we can look through here. It's definitely not A or C because we have an oxygen here, a bromine and a chlorine here. It isn't a carboxylic acid, nor is it an ester over here, which means it could be between B or E. And if we're going to look at E off the bat, ethine is meth eth, so we got 2 C's here. There are only H's, there's no attachment groups, and then there is a triple bond. And unsaturated hydrocarbons have double or triple bonds, so therefore E is our answer here for 2.6.1. And that would earn us 1 mark over there. And then 2.6.2 says the compound with the general formula CnH2nO. So if we're going to reference the sheet here, we can see the general formulas for all of these guys. So if we're going to go ahead and see CnH2nO, we're dealing with either an aldehyde or a ketone over here. It isn't an alcohol because that would be an OH on the end. It also isn't a carboxylic acid like D because we'll have 2 oxygens over there. As you can see, carboxylic acids and esters will have the same amount of everything, same amount of C's, H's, and O's, just in a different arrangement. That's why they're functional isomers, which means that we have to look for either an aldehyde or a ketone. And we didn't see any aldehydes in this example. We had to draw one earlier, but we are dealing with A here again because this is our ketone. It has a general formula of CnH2nO. So we can just go ahead and write A over there, and that would earn us 1 mark over here. And then 2.7 says, using molecular formula, write down a balanced chemical equation for the combustion of compound B, so compound B over here, in excess oxygen. So this is a very common question. They like the combustion reaction in the presence of oxygen. And it's quite a nice one for us, especially if we do life sciences, because it's just like breathing for humans. So first off, molecular formula, we can't just write it like this because this is a condensed structural formula. This is the condensed version of drawing something out like this. So that means we're just going to have to go ahead, count the total amount of C's and H's, and then we can take it from there because we have 1, 2, 3, 4, 5. We have 5 C's over here, and then from there we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we have 12 H's over here. If ever we were to draw this B, this little portion in brackets would be a side chain. That's always something to note. Anything in brackets is a side chain. But right now, we don't need that for the molecular formula, so we're writing down the balanced chemical equation for the combustion of compound B in excess oxygen. So if it is in the presence of excess oxygen, it means that it will be reacting with oxygen on the reactant side. So we have O2 over here, and that is going to go to, just like humans breathing, CO2 as a byproduct, or like a fire burning, CO2 is being released after we're burning up oxygen. That is what combustion means. And then we also release water. So we have H2O over here. So we're just going to go ahead and balance it now because we have our molecular formula in the presence of oxygen going to CO2 and H2O also in molecular formula forms. And if we're going to count the amount of C's, we have 5 C's over here. We have 12 H's, and then we have 2 oxygens. Cool. And then on this side, just aligning our C's, we have 1 C. Then the H's we have 2 H's. And then we have 3 oxygens. So a general rule of thumb is try and balance your C's first, and then your H's and O's will take care of themselves, especially the oxygens, because we have this lone oxygen here that we can add any numbers to balance it. So if we start with a 5 here in front of our CO2, we'll turn this 1 into a 5, and then 5 times 2 is 10 for the amount of oxygens, and then plus 1 over here. So we have 11 oxygens here now. So our C's are balanced, which is great. Our H's are not balanced. So let's take care of them next. So if we put a 6 in front of our H2O here, we have 12 H's in turn, which is perfectly balanced. And then we just have to go ahead and recount our oxygens, because then we have 10 oxygens here and 6 oxygens there, which means we have 16 oxygens in total. So the C's are balanced, the H's are balanced. This last move is quite easy for us then, because all we have to do is add an 8 in front of our O2 here, because 8 times 2 is 16. There's no other oxygens on this side. Then we have 16, and we've balanced our oxygens like that. So therefore, C's are the same, H's are the same, and oxygens are now the same as well. And the balancing would earn us our 3rd mark, so therefore we got 3 out of 3 over there. And then last question over here, 2.8 says, a compound is analyzed and found to have an empirical formula, so the simplest representation of CH2O. The molar mass of the compound is found to be 150 grams per mole. That is the actual molar mass of the molecular formula. It's saying what is the molecular formula of the compound. Usually this last question is either determine the empirical formula or doing some sort of molecular formula ratio, which is exactly what we're doing now, because what we're doing is a ratio of the molar mass of the molecular formula over the molar mass of the empirical formula. And we're always going to get a nice whole number here, And that means we're just going to have to multiply all the numbers by whatever number we get in this ratio, because the molar mass of the molecular formula, as we've seen, is 150. And then the molar mass of the empirical is what we have to calculate. We can just do that from the periodic table, or if we know the molar masses of each of these elements, we can just add them up, because carbon is 12 plus hydrogen is 1, so 1 times 2 is 2, plus oxygen is 16. So we can get all of this from our periodic table, but what we have then is 150 over 30, and this looks like a nice clean number for us, which means we've done our calculations correctly, because 150 divided by 30 on our calculators is 5, which means that all we have to do is this guy. We have to multiply everything by 5. We don't just put 5 in front of the whole thing. It's not like moles. We have to update the numbers, the amount of each element inside of this compound, which means if we are multiplying this by 5, we end up having a molecular formula, the actual formula in nature, not just the simplest representation. We have C5H10 and then O5. So we have C5H10O5, and that would earn us 2 marks over here and 21 marks for this whole section. Question 3, where we're going to look at boiling point and the common patterns in this section. So question 3 says, during an investigation, a table of data was collected for 4 organic compounds, A, B, C, and D, as we have over here. The compounds have different functional groups, so that is how we're distinguishing things. We usually compare one of 3 different factors, either the chain length, or the types of bonds. In this case, considering there are different functional groups, they'll have different types of bonds, and then bond order, which is less common than the first 2. So we usually just compare one or the other. What we're going to see here is that they usually have the same amount of C's if we're just going to compare the different functional groups and the different types of bonds. But let's see what's happening here. We have A, which is a straight chain with just C's and H's, and we have the molar mass over here and the different boiling points, which links to the strengths of the types of bonds. From there, we have a CHO over here. So this is some sort of aldehyde where we have a C with an O and then an H over there. And then this third one, C with a COC over here in the middle. And then, as you can see here, for D, we have a COOH. This is some sort of carboxylic acid. And the molar masses, they are the same for A, B, and C. D is a little bit bigger, and the boiling point gets progressively higher from A to D. So 3.1 says, define the term boiling point. So boiling point is quite a common definition in this section. It's either that or vapor pressure, but the boiling point is the temperature at which the vapor pressure of a substance equals the atmospheric pressure. And that would earn us 2 marks here. This is just something on our definition sheet for our exam guidelines, and this is an all or nothing question, so we have to get all the key words here to get the 2 marks, or we'll get 0. So that would earn us 2 marks. And then 3.2 says, in the investigation above, name the independent variable. So we wrote these 3 guys up here in the beginning, the chain length, type of bond, and bond order, because these are usually one of the independent variables. So they'll usually do this question in some sort of investigative question type way, where we have independent variables. It's either chain length, type of bond, or bond order. And then the dependent variable is the boiling point, because what can happen is that we can change either of these. We control the chain length or the different molecules based on their chain length, or the molecules we're choosing to investigate based on their types of bonds. And then because of that, because of them having different types of bonds in this example, they'll have a different boiling point. So boiling point will always depend on one of these 3 guys. So we just need to keep that as our frame, because in this investigation above, name the independent variable for 1 mark. It is organic molecules with different functional groups. As we can see here, these compounds have different functional groups. That is what we're controlling. Either this or the homologous series is another way of saying that, because as we change homologous series or molecules with different functional groups, we'll get different types of bonds over here, which means this would earn us 1 mark for 3.2. 3.3 says, explain the trend in the boiling points among A, B, and C as shown in the table above. So just A, B, and C based on them having the same molar mass, even though they have different amounts of C's. A has 1, 2, 3, 4, 5 C's, B has 1, 2, 3, 4 C's, and C has 1, 2, 3, 4 C's as well. So on this sheet over here, we're going to compare A, B, and C as they mentioned, and we're just going to reference this organic molecule sheet so that we can see what type of bonds we're dealing with. Because if we have different functional groups, we have different types of bonds, and we just need to see what type of bonds do they actually have so that we can compare them. There's a very standard format for these types of questions, so we're just going to check that out. So as we established, this is some sort of hydrocarbon as there are only C's and H's. There aren't any double bonds or triple bonds if we were to draw this out. So this is some sort of alkane over here. And as we can see for alkanes, based off the intermolecular forces here, they only have London forces. There aren't any dipole-dipole forces because there are only weak London forces between the H's and the C's. And then B over here, as we established, is a CHO, like we have over here for our aldehyde. We have an aldehyde over here, a CHO, and that has London forces, but also dipole-dipole, and that is a dipole-dipole force between the oxygen and the carbon atoms. And then C over here with a COC in the middle, which also has London forces and dipole-dipole forces, because there's also the interaction of dipole-dipole between the oxygen and the C's. So these guys don't have any hydrogen bonding. That is only for a carboxylic acid and an alcohol because of the H directly attached to the O, and that is what hydrogen bonding consists of. Hydrogens interacting with nitrogens, oxygens, or fluorines being directly attached. And we can see that here when it comes to D, because D has a carboxylic acid and that has a hydrogen bond, and we can see that the boiling point is significantly higher for it. So that means if we know which compounds we're dealing with, we can just break down what type of forces they have, and then we can compare the trend in boiling point. So we can start off by saying that B and C both have dipole-dipole forces because of the O attached to the C for both of them. Next, we can discuss what type of forces A has, and it has weak London forces because there aren't any other elements besides the carbon and hydrogens. So A has weak London. This would earn us 2 marks so far, and then we just have to compare all of these guys to each other, that the IMF, the intermolecular forces in C, is stronger than B, stronger than those in B, and the weakest in A. And we can see that here with the boiling point going from 36.1 to 74.8 to then 79.64. The same molar mass, but because of these different functional groups, the ones that we just compared, there's a different boiling point for each of them. In spite of different chain lengths, we're ignoring that because they are telling us just to compare the functional groups. And we say, therefore, C will require more energy to overcome the IMF, to break the intermolecular forces, so to overcome IMF between molecules A and B. Between molecules, then in B and A. So more energy required to overcome the IMF in C here compared to B and A over there. And that would earn us 4 marks over here and is the standard trend, what they want when we are comparing different molecules with different functional groups, saying which intermolecular forces they have, which one is stronger, and then therefore more energy to overcome the intermolecular forces of the stronger one or the one with the higher boiling point. Because we have a higher boiling point because we require more energy. Boiling point and energy are directly proportional, so therefore the higher the boiling point, the more energy is required for the bonds to actually break between these molecules. And then 3.4 says, which compound C or D would have the lowest vapor pressure? Give a reason for the answer. So the lower vapor pressure between C and D over here is what we're looking at, and something to note is boiling point and vapor pressure are indirectly proportional, which means if boiling point goes down, vapor pressure goes up. If boiling point goes up, vapor pressure goes down. This is just something we have to know. If we want to understand why, we can see this bottle analogy over here, where we have a plastic bottle in a car, and when the car warms up, the bottle expands. Obviously not to this degree, but if we had 3 little dots of water left inside this bottle because we didn't drink it after practice or anything, and then the bottle expands in the hot car, so the boiling point goes up, the temperature increases, we have these same 3 little dots over here. And what happens is there's a little link in between these two, is that the volume increases because there's more space, not the volume of the little dots, but the volume of the space of the container that those dots are in. And because the volume has increased, the pressure, how many collisions between these guys, decreases. And that's why boiling point and vapor pressure are indirectly proportional because of this explanation. But this is something we can just remember if that's easier, but this is why it works, because in the other scenario, if boiling point decreases from the big bottle to the small bottle, the volume decreases. The boiling point decreases, volume decreases, the container gets tighter, and then pressure, the amount of collisions between these 3 dots, happens more frequently. And there'll be more collisions, more pressure inside of this one. So then, with that being said, which compound, C or D, would have the lowest vapor pressure? The lowest vapor pressure would be the one with the highest boiling point. So therefore, D is our answer, and that is because the highest boiling point will have the lowest vapor pressure. And that is all we need to say for this one for 2 marks. And then 3.5 says write down the following. 3.5.1, the phase of compound A at room temperature. So compound A is over here and room temperature is 25 degrees Celsius, which means that the boiling point is a little bit above 25 degrees Celsius. It's 36.1 over there, which means that boiling point implies the change from a liquid to a gas. So only above 36.1 degrees Celsius will it become a gas, start changing from a liquid to a gas. They haven't spoken about melting point over here, which means that the phase of compound A at room temperature is a liquid, just because it is below 36.1, which means it is not a gas yet. Only if it were above 36.1 would it be a gas, but room temperature implies 25 degrees Celsius. So that just earned us 1 mark over there. And then 3.5.2 says the structural formula of the functional group of compound B. So we're going to have to draw this, and we're just going to draw the functional group of B over there. And just like we saw in that picture earlier, it is a CHO, it is an aldehyde. We're dealing with a C with a double bond O over here with an H attached on it. And then all we have to draw is the 4th line here, 1, 2, 3, 4, and we're happy. This is the functional group, the specific key to place this organic molecule as an aldehyde. So that just earned us 1 mark over there. And then last question, 3.5.3 says write down the IUPAC name of compound C. So IUPAC name of compound C over here. So I'm going to draw it for us quickly, a ketone, because a ketone is very similar to an aldehyde. As we can see over here, the ketone is a C double bond O in the middle, and then an aldehyde is a C double bond O on the end. So there's availability for an H over there to attach to that C as well, which means that we know we are dealing with a ketone with our C double bond O in the middle, which means a ketone just ends with an "-one" over here, and the naming convention also ends with an "-one" over here for the suffix, which means that all we have to do is that we have to write the amount of C's that we have, and then we'll be good to go. Because if we can count the amount of C's, we have 1, 2, 3, 4. So we have meth, eth, prop, bute. We have bute, and then we have our O on the second C over here. So if we're going to draw it, we have 1, 2, 3. We have a C over here. We have our double bond O. Then we have a C again with 2 H's, another C with 3 H's over there, and that is everything. So as we can see, we have our double bond on the second C over here. So we have meth, eth, prop, bute. So then we have butan 2-one, and we can't just say bute 2-one. We always need the an over here, otherwise we won't get the marks. So butan 2-one will earn us 1 mark over there and 12 marks for this whole section. Question 4. So this is the types of reactions question over here for organic chemistry. So it says 4 bottles containing organic compounds are found in the lab. The chemicals are used in various reactions. So we have A over here is a primary alcohol, B is a secondary alcohol, C is propene, so a double bond over there, and D is propanoic acid, a carboxylic acid. So 4.1 says identify the type of reaction that occurs when each of the following reactants are used: bottle A and bottle D. So we have an alcohol and a propanoic acid, so our carboxylic acid. So a very common reaction, as we can see here on the sheet, for a carboxylic acid and an alcohol is esterification, because carboxylic acids with alcohols will form esters. So this guy plus this guy equals an ester over here, which means we can just call this esterification. It isn't an addition, substitution, or elimination reaction. It is a condensation reaction, but it's much easier if we just call it an esterification reaction. So we can just go ahead and write esterification, and that would earn us 1 mark over there. And then they're saying bromine water and bottle C. So propene, meth, eth, prop, we have 3 C's over here. And as we established, it has a double bond because it's an ene. So ine would be triple, ane would be single, ene is double. And we have 4 lines around each of them. So propene and bromine water is a Br2. And something to keep in mind for something like this is that this is an addition reaction. We don't have to know specifically which type it is. It is halogenation because we're adding a halogen to a double bond, but addition is always going from 2 to 1. And by that, I don't just mean the amount of elements on each side. We do have 2 compounds here. They are going to form 1 new compound over here because this double bond is going to break. And when it breaks, we're going to get availability for the 2 bromines to attach over here and over here, which means we are going from 2 compounds to 1 compound. But the easiest thing to look at, especially for flowcharts in this section, is to see that we're going from a double bond to a single bond. Our double bond has to break for an addition reaction to occur. That's how we see whether it's addition, substitution, or elimination. So we can say bromination or halogenation, but for these ones, if they don't ask for the specific type of reaction, we can just go ahead and write addition, and we'll earn our 1 mark over there. And then 4.3.1, bottle B over here, the secondary alcohol and concentrated sulfuric acid. So we have a secondary alcohol, something like this, where we have 2 C's attached to the C that the hydroxyl group is attached to. So 1 C, 2 C's are attached to the C that the hydroxyl group is attached to, and that is reacting with concentrated sulfuric acid. And one thing to note is that sulfuric acid is usually some sort of catalyst that we have on our line. So we have heat for the most part, and then we have concentrated H2SO4. And H2SO4 for an esterification reaction as well as this reaction, is some sort of dehydrating agent, which means that we are trying to remove this OH over here. And in turn, if we're going to remove it, we are going to form a double bond, because then we have something like this. We have formed our double bond over there because we have removed the OH. And the H and the OH that we're removing is H, H, and O. So we have 2 H's and an O, which becomes H2O. So we have that, and then we have the remaining C's, just like we started with over here, which means we have the remaining C's plus H2O. This H will go with that OH, and we are removing it because of the H2SO4. It's not getting involved, but it is causing this reaction to occur. And something to keep in mind is that this is exactly the opposite of an addition reaction, because an addition reaction goes from 2 to 1, and here we have 1 going to 2. And by that, I don't just mean the amount of compounds again, I mean going from a single bond to forming the organic compound with a double bond. So the opposite of addition is an elimination reaction, and that is what we're dealing with over here, because we eliminated the H2O and we have formed something with a double bond. So it's not substitution, that would just be swapping something, and we aren't just swapping something, we are forming a double bond over here. And elimination and addition are exactly backwards. Addition going from 2 to 1, double bond to a single bond because it has to break. Elimination is removing something. So because we've removed something, we have to form a double bond that our organic molecule is satisfied. And there are 4 lines around each C. So we can just go ahead, write our elimination over here, and that would earn us 1 mark over there. This is dehydration. We are removing water, so that is dehydration specifically, but it is an elimination reaction. We can just keep the general type of reaction over here. So then 4.2 says, give the structural formula, draw the formula of the alcohol in bottle B if the alcohol has a prefix of hex. So we're going to have hexanol. So this is a secondary alcohol, hexanol. As we were discussing earlier, a secondary alcohol has 2 C's attached to the C that the hydroxyl group is attached to. So starting with the hex portion, we have meth, eth, prop, bute, pent, hex, and then we're going to have our lines around here for all of our different hydrogens. We're just going to see where we need to attach our hydroxyl group, our OH, because this is an alcohol. So a primary alcohol would be attached to the end over here, which isn't what we want. We're just eliminating things because there's only 1 C attached to the C that the hydroxyl group is attached to, which means that making the change of where to add the hydroxyl group if we want a secondary alcohol is quite simple, because all we need to do is add our OH over here. It could be here as well. It could be really anywhere, just not on the end, because over here in this location, we have 2 C's attached to the C that the hydroxyl group is attached to. And this would be perfect, which means we can put it on the 2nd C or the 3rd C. Once again, this would be the 3rd C from the right or the 2nd C from the right. Either way is the same as long as there are 2 C's attached to the C that the hydroxyl group is attached to. And that would earn us 2 marks over there. In the test, write all your H's around your C's, but for now, we're just trying to focus on the placement of the functional group, because then 4.3 says, use structural formula to represent the chemical equation for the formation of the ester called butyl propanoate while using the primary alcohol in bottle A. So butyl propanoate is the name of the ester that we are writing. We are doing an esterification reaction, a different one from 4.1.1 where we did bottle A and bottle D, but we are looking at which reactants we need and what product will be formed. This is a very common question that they ask. They really like esterification questions. So something to keep in mind is that the butyl always came from the alcohol. That means we'd have to have a butanol over here for our alcohol. The propanoate always comes from our carboxylic acid, which meant propanoate came from our propanoic acid. So we have our oic over here. OH turns to oic, and we have propanoic acid. So that means we know we have an alcohol, a butanol, and a propanoic acid. And then we have our ester over here, and we'll have to know what the other product is as well as the catalyst. So let's start with the alcohol portion. So we have meth, eth, prop, bute, and then it is the primary alcohol in bottle A, which means that our alcohol will have to be on our first C, so that only one C is attached to the C that the hydroxyl group is attached to. So we have this guy over here, OH, like there. Doesn't matter whether it's drawn here or down as well, as long as it's on the first C or this first C over here. This is going to be reacting with propanoic acid. We have meth, eth, prop. So we have 3 C's, meth, eth, prop. Propanoic acid has a double bond O with an OH over there. It can be on this 1 C over here or on this side, but meth, eth, prop, we have 3 C's with our COOH over there. So on our line over here, we're going to have heat and we're going to have H2SO4 as well. And then, like we were discussing, we have to write our ester. So what we're going to do is we're going to have our 4 C's from our alcohol. So 1, 2, 3, 4, like that. We're going to have this O over here, which is going to make the oxygen bridge between these two molecules. And then what we're going to do is we're going to attach this C over here, this C, and then this C. So we have our 3 C's on this side. We have our oxygen bridge down the middle. And then what we need is that the double bond O is always from the propanoic acid side. So we have our double bond O over here on the propanoic acid side. Then we can just go ahead and draw all our H's around there, draw all the H's around the C's, and over here we'll have our meth, eth, prop, bute. We'll have our butyl, and then meth, eth, prop, propanoate, like this name that we started with over here. And then one thing to keep in mind is that just like H2SO4 was used in our elimination reaction earlier for bottle B with concentrated sulfuric acid, H2SO4 is a dehydrating agent over here, which means that it has removed this H and this OH over here, which means H2O has been removed in this reaction. So we have that as a product as well. And that would earn us 4 marks over there using structural formula to represent the chemical equation for the formation of this ester, butyl propanoate, while using our primary alcohol over here. Then for the other 2 marks, it does say include the IUPAC names for the reactants specifically. And we almost had them up here when we were writing. We have our propanoic acid, so that's great. And then we just need to update our butane over here, because what we have is butan 1-ol. We just have to write the number of the location of where the hydroxyl group is attached to. And with that, we'd earn the additional 2 marks over there. And this would earn us 6 marks in total. Then 4.4 is a follow-on question. It says concentrated sulfuric acid is added to the reaction in question 4.3. So what we just discussed here with the H2SO4. What is the function of the acid? So it is a catalyst. It helps speed up the reaction without getting involved by lowering the activation energy. So therefore we can apply some heat and this reaction can take place a lot quicker. So we're just going to write catalyst here. Other memos say that we can call it a dehydrating agent, but it does serve as a catalyst for this reaction to speed up, happen more quickly. So that would earn us 1 mark over there. And then 4.5 says, give the name of the functional group for bottle B. So bottle B is a secondary alcohol, and that means we're dealing with this OH over here. And the name of the functional group for bottle B is called a hydroxyl. That is what we call that OH attached to it. That is the specific key that makes the whole organic molecule an alcohol. So if we write hydroxyl over here, that'll earn us 1 mark over there. And then 4.6 says, bottle C is used to produce an alcohol. So propene over here. Name the reaction conditions required. So bottle C is a propene. So we have meth, eth, propene, like this. And this one is very similar, but backwards, to our elimination reaction over here, where we eliminated H2O in our H2SO4. We formed our propene over here, and that came from our propan 2-ol over here that we had. So this guy is just working backwards from this guy, which means that if we have a double bond, it is some sort of addition reaction, and it is reacting with H2O over here. And then we'll break this double bond so that we can add our water over there. So we have C, C, C. The 1H is going to join here. And then the OH, the remaining portion of the water, is going to join over here. So we'll just reference this as we answer the questions, but it is saying 4.6.1, name the reaction conditions required. So what we need for this is we need water to be present. As we can see over here, we need water. And then we usually need a strong acid for addition reactions because we need some sort of catalyst to lower the activation energy, because breaking double bonds or forming double bonds requires a lot of energy. So we need water and we need concentrated sulfuric acid. We could also use phosphoric acid. It's just generally easier to use sulfuric acid as it's quite a common catalyst in many reactions. So knowing those two conditions, that would earn us 1 mark over here. And then 4.6.2 says, give the structural formula of the major product that forms. The major product that forms will in fact be this guy over here. But what we're going to distinguish is the difference between a major product and a minor product. Because when this double bond breaks over here, and we open up this availability to attach our H to one and our OH to another, we're not quite sure whether the OH will go on the 2 or on the 1. Because there can be different arrangements. It can be on the 2 or it can be on the 1. But there's a rule called Sukhovnikov's rule, which means when a double bond breaks, the carbon with the most H's, so here we have 1 H and 2 H's, compared to this carbon over here, which only has 1 H over there, the carbon that has more H's will get the H. There's a memory device that says the rich will get richer, and that means the carbon that has more H's will then get the H over here. Compared to the minor product means the carbon with less H's will end up getting the H. So if it said minor, we'd put the H over here, and then we'd put our OH over here on this guy. But it is saying major, and major means that the carbon with the most H's, because we now have these two availabilities here, the carbon with the most H's, so 2 over here, will get the H, and that means this carbon here with fewer H's will get the OH over there. So it will get the functional group of the hydroxyl attached to it over there. And that is how we draw the structural formula of the major product that forms. So we have a meth, eth, prop, propan, 2-ol over here, compared to the minor product where these guys would swap, and that would be propan, 1-ol. And that would earn us 2 marks over there. And then 4.6.3 says, name the type of addition reaction that occurs. So here they want the specific type of reaction. We can't just say addition. They want the specific type of addition reaction. And as we established, we were adding water. So if ever we're adding water, that is called a hydration reaction. If we are removing water, that is a dehydration reaction when it comes to single bonds and double bonds. So an addition reaction, double bond is going to break. We're going to react with water to form an alcohol. An elimination would be dehydration, removing the water, and then we are going to form a double bond over there. So for 1 mark, we can just write hydration, and then 4.6.4 says 2 products are formed during this reaction. The products can be separated through distillation. Which property of the compounds allows this separation? So this one's a bit strange because as we can see, there is only 1 product over here, but it doesn't have to do with the alcohol plus something else being released. As this is an addition reaction, the propene plus the water in this case forms our alcohol over here. But what they are talking about is the arrangement of either a major product or a minor product. Whether we have our OH over here on the second one, or whether we have our OH over here on the first one instead of the second one. And because of the location of the functional group, if it's on the first one, the boiling point is usually higher. If it's on the second one, it's usually less high because the surface area is less, which is just an additional thing. We don't have to know that in depth, but the 2 products, they are referring to the major or the minor product, whether the hydroxyl is on the second carbon or the first carbon, and these products can then be separated through distillation. So we can extract the different type of alcohols out from one another when they are forming in large quantities and are mixed. And it says which property of the compounds allows this separation. What we can write is by using their boiling points, because they will have different boiling points because of the location of the functional group, which means we can just use their different boiling points, and therefore we can separate them, distill them, and get the type of alcohol that we want and remove the type that we don't want, and then collect both of them individually. So by using their different boiling points. And that would earn us 1 mark over there and 18 marks for this whole section. Question 5, the rate of reaction question. So question 5.1 says, define the term heat of reaction for 2 marks. So this is an all or nothing question. The heat of reaction is the energy released or absorbed in a chemical reaction. And that would earn us 2 marks over there. This is an all or nothing question, just something we have to know from our exam guidelines. So something we'll have to memorize, but the heat reaction is something that is released or absorbed in a chemical reaction. And then 5.2 here says, the reaction between sodium thiosulfate and hydrochloric acid is investigated. A conical flask, as we can see over there, is placed over a cross on a piece of paper. The time is measured from the moment the acid is added to the sodium thiosulfate until the cross disappears. So we just have the cross underneath so we can monitor how long it takes, rate of reaction, for it to disappear. So the equation of the reaction is given as follows. We have Na2S2O3 plus 2HCl goes to 2NaCl plus H2O plus SO2 plus S solid. And we can see that we have our delta H, which is greater than 0. And what this means is that we have an endothermic reaction. So we have endo versus exothermic. Something like this, for example, would be exothermic, because here are our reactants and here are our products. And here on this side is our potential energy in terms of heat. And imagine this number was 10 over here and this number was 5 over here. The reaction for enthalpy is delta H, and that equals E of products minus E of reactants. And if we're going to plug in these values we added, E of products, we have 5 over here. And then for our reactants, we have minus 10 over there. And this will give us negative 5 kilojoules. And this is a negative value, which is delta H, which is less than 0, i.e. negative. So all that means for us is that this delta H is positive, so the shape is exactly the opposite. Those are our reactants, those are our products, and it is just a different shape, meaning endothermic is taking in heat, and exothermic over here is releasing heat. So we'll see how we need to place that when we go forward, but it does say the reaction is carried out with solutions of different concentrations of sodium thiosulfate. So we have different reactions with different concentrations of our sodium thiosulfate over here. The table below shows the data collected. We have concentration of Na2S2O3 in terms of mol.dm to the negative 3. It's always helpful in this section to see what we're measuring in terms of mol.dm to the negative 3, and that's our concentration. So we have our concentrations over here, and then it says time taken until the cross could not be seen in seconds. So we have the cross over there. We're trying to see how long until it cannot be seen. Okay, in seconds. So we have trial 1, we have the different values here. Trial 2, the different values. Trial 3, and then the average of all of them, which is very important when it comes to rate of reaction, is to take the average, especially if we're doing multiple reactions. So then we have 5.2.1 over here, and it says identify the independent variable. So the independent variable is the thing that we can change. And the rate of reaction section usually has to do with an investigation type question where we have our dependent variable. We have dependent over here, and we have our independent. So those are the things that we can change. So the dependent is always the rate of reaction, because we're going to manipulate something so that we can then in turn affect the rate of reaction. And then our independent are the things that we control, as we mentioned. And there are usually 4 different things that we can impact in order to speed up a reaction. That is what rate of reaction means. The first one is concentration. That's what we're dealing with right now. As they mentioned in the table, we have the concentration of the Na2S2O3. Then we can have surface area. So surface area means if we have some sort of powdered state of magnesium versus magnesium ribbon, the powdered version will react quicker because there's more particles exposed. So concentration, surface area. We have temperature as well, because if we increase the temperature, we'll have more effective collisions per unit time because we would have increased the kinetic energy. And then last one is a catalyst. It doesn't increase the kinetic energy or increase the amount of particles like surface area and concentration, but a catalyst does lower our activation energy so that the reaction can take place quicker. So these are one of the 4 independent that we'll be testing in this sort of investigation: concentration, surface area, temperature, and catalyst. And in this scenario, we are measuring concentration. For 5.2.1, we can just write concentration of Na2S2O3. And that would earn us 1 mark over here. Because then 5.2 says calculate the average rate of reaction in mol.dm to the negative 3, as we have over here, dot S to the negative 1 for the highest concentration used. So the rate of reaction formula is something we'll always have to unwrap from the units given, because we have average rate of reaction over here, and this equals the mole.dm to the -3 over time, because that's what it means here, mole.dm to the -3, like we have our concentration over here, but s to the -1 means our seconds is at the bottom. We're dividing by seconds because if we're going to take it to the top, then it will be multiplied by s to the -1. So they can always give us any different units here. They could be concentration, they could be mass, they could be anything like that. And then it could be in seconds or minutes or hours. It depends. So we just need to write the formula based off of the units that they gave us over here, which means they did say for the highest concentration used, which means that the highest concentration was 0,080 for our mole. We got 0,080 over there. And then here we have time in seconds. So that's good for us. We don't have to do any conversions to minutes. And then we will actually have to calculate our x value here, considering we do need the average. So in order to calculate the x over here, we can just go 31 plus 41 plus 33 divided by 3 over there. And if we plug this in our calculator, we'll get 35 seconds over here, which means we can just go ahead and plug this in over here. So we have 35, and this equals 0,0023 mole.dm to the -3 times s to the -1, just like the units they put over there. That would earn us 3 marks over there. And then 5.2.3 says, give the reason for the disappearance of the cross. So we have the disappearance of the cross, just as they mentioned at the start of the investigation, this whole cross would disappear. Okay, it won't dissolve, it is underneath, but why won't we see it? So this has to do with the state of the products. So over here on this side of the arrow, we have our different products. So we had our reactants Na2S2O3 over here and 2HCl over there. These guys react, they are both aqueous solutions, but then we form the products 2NaCl, also an aqueous solution, H2O, a liquid, SO2, a gas, which will then escape outside of our beaker. But lastly, we have our sulfur over here, that's a solid. So 2 aqueous solutions are clear for the most part, they're visible so we can look through them. But if we are forming a solid, as this reaction is taking place, the solid will start to cover up the cross and will reduce our visibility until the cross has entirely disappeared. So all we have to write for 1 mark here is the sulfur is a solid and covers the visibility of the cross. And with that, that would earn us 1 mark over here as this whole precipitate starts to turn murky with liquids, aqueous solutions, and solids all together. Therefore, we won't be able to see the cross over there. And then 5.2.4 says, use the collision theory and explain the trend observed in this experiment. So as our concentration increases over here, our rate of reaction, or the average rate of reaction, decreases from 69 to 44 to 35. So using collision theory, a very common question, we have to explain with 3 main points this trend observed, that as the concentration increases, the rate of reaction decreases. So number 1 for us, we say concentration increases, and therefore the number of particles per unit volume increases. So the best way to describe this is, say now we have water over here, and then we pour some Oros into our water. So now we pour 3 little droplets. So our concentration is only so much. Let's say it's the 0,040 over here. But then as our concentration increases to 0,080, so let's add 3 more dots because that's double over there, we have more concentration, therefore more particles per unit volume. This is the same volume, the same amount of mixture, the aqueous solution that we're referring to up here. So it's the same volume, but now we have more particles in that same volume over there. Which means that because we have more particles in that same volume, we'll have more effective collisions per unit time. So because there are 6 dots here instead of 3 dots, as they move into each other and collide, there will be more effective collisions in the same time. So we're timing it, and for 3 dots, there will only be so many collisions until we convert top left again here from these reactants, the Na2S2O3 plus 2HCl, to these products over here. So that's what the effective collisions are about for collision theory. As the reactants collide, the Na2S2O3 and the 2HCl, we end up forming these products over here. And now because there's more of a substance, more particles, there'll be more effective collisions colliding together in order to form those products over there. And then last link in the chain, just because it's all about how the independent variable affects our dependent variable, how the concentration, like we started with, affects our rate of reaction, and therefore the rate of reaction will also increase. And these are the 3 steps that we need in order to get our 3 marks over there. And then 5.3, the last question over here, it says the activation energy for this reaction is 27,3 kilojoules. So like we had here, delta H is greater than 0, so we're dealing with some sort of positive endothermic reaction. And now they've given us the actual value for the activation energy of it. So what we have here, 5.3.1 says define the term activation energy, and this is also from our definition sheet, and it is the minimum energy needed for a reaction to take place. And this is an all or nothing question again, like all definitions. So we just earn 2 marks over here with all of these keywords. And then 5.3.2 says draw a fully labeled sketch graph of the potential energy graph for this reaction. So like we established, this is endothermic. If we're going to look all the way up here, again, it will be some sort of shape like this. So now they've just given us the activation energy from the reactants to the products, to the peak, in order for these reactants to convert to products. So we're just going to redraw this and then label it correctly, and we'll earn our 2 marks over there. Because we have our border over here, the potential energy, I'm just going to write EP over here, but we would write potential energy. So that would be our y-axis. On the x-axis over here, we have the course of the reaction, just the time that we're measuring to see how we are converting from reactants to products. And then because we have our delta H is greater than 0, we know that our shape is endothermic, with the products being a bit higher than the reactants. This would earn us the marks for the shape over here. The activation energy, as they mentioned here with the 27,3 kilojoules, is from the reactants over here all the way up to our activated complex, the peak over there, in order for these reactants to convert into products. Because as soon as we have enough energy, these reactants will convert into products, and there will be the Na2SO3 over here, and the 2HCl will convert into the 2NaCl plus H2O plus SO2 plus sulfur over there, which means we do have to draw this line over here, and then we're just going to label it as EA equals 27,3 kilojoules, as they mentioned over there. And then the last label, we can just draw a dotted line over here, straight in line with our reactants, and then labeling it from the dotted line all the way up to our products over there. We can call this our delta H, like we were chatting about earlier. The enthalpy, which will be the E products, these guys, minus the E reactants, these guys, in order to get a positive value over there. And that would be everything we need to draw a fully labeled sketch graph of the potential energy graph for this reaction, earning us 2 marks over there and 14 marks for this whole section. Question 6, chemical equilibrium. So question 6.1 says, consider the following chemical equilibrium. So we have our 2Cr O4 2 negative aqueous solution. They're telling us that the solution is yellow when there's more of this present. We also then have 2H plus aqueous solution, and we have our double arrows implying chemical equilibrium, which means that the reaction can go both ways, either forward or backwards. And then we have 2Cr2O7 to the 2 negative, and when the solution is orange, there will be more of this present. And that is also an aqueous solution, plus H2O liquid is just a byproduct. And then they've also given us our enthalpy over here, this delta H, and it is negative 895 kilojoules per mole. So if we have a graph like this, we're dealing with some sort of exothermic reaction, because here we have our EP, here we have the course of reaction, or we can just call it time, and here we have our reactants, and here we have our products. Okay, if we're gonna put a number value here, let's call this 10 over here, let's call this 5 over here. Our delta H is our E of our products minus the E of the reactants, which means that the product's value is 5 over here and the reactant's value is 10 over there, and therefore we have a negative 5. And if something is negative, it's implying that it is exothermic, like this. But what's most important for us when we have an exothermic reaction is that we are releasing heat. So we're going to plus heat on this side where our products are, so we can then deal with any changes that might happen to this whole beaker. Because what's happening is that this reaction is taking place inside one beaker over here, where we have our reactants and our products, and depending on how we affect the reactant side or the product side will determine whether the forward reaction is favored or the reverse reaction. Because this leads us into 6.1.1, where it says what is meant by the term chemical equilibrium. And for 2 marks, it is when the rate of the forward reaction equals the rate of the reverse reaction. That means the forward reaction equals the reverse reaction, which means as these ones over here form new products, these ones over here break down to form the reactants at the exact same rate. And this would earn us 2 marks over here. And then 6.1.2 says, using Le Chatelier's principle, explain how an increase in temperature will change the color of the solution. So as we established, this is all inside one beaker. So we have our reactants and our products and our heat all being released in one beaker. And the reason we wrote heat like this was because heat is greater on this side. So if we're going to move it over here, we can treat heat just like we would a reactant or a product. And if we're increasing the heat in this whole beaker, therefore we would have more heat on the side. And what happens is if we have more heat on the side, imagine there was a ball on a seesaw over here. We've increased the heat on that side. The ball has to roll downhill in order to favor the other reaction, which means that if heat is increased on our product side, it means the reverse reaction is going to be favored because we have more heat. We've increased the heat and therefore it needs to favor the reverse reaction to counteract this disturbance. So we start this by saying, according to Le Chatelier's principle, an increase in temperature favors the endothermic reaction. So as we established earlier, this is an exothermic reaction going forward because we have our reactants which have a higher potential energy than our products over here. But then if we've increased more heat on our product side over here, it means that the reverse reaction is going to be favored and therefore it will be favoring the endothermic reaction. Because the forward is exothermic, heat has been released and therefore adding more heat will favor the reverse reaction, which leads us to our second point, saying the reverse reaction is favored. And then in this specific question, they were asking the change of color of the solution. How will that affect it? And as we established, it will be orange if the forward reaction was favored, but if the reverse reaction is favored, it will form yellow, which means we just have to write that the color of the solution changes yellow. And that is how we'd use Le Chatelier's principle with these 3 steps to earn us 3 marks over there. And then 6.1.3 says, a concentrated solution of hydrochloric acid is added to the equilibrium mixture. What is the effect on the concentration of the dichromate ions, the Cr2O72-? So this guy over here, Cr2O72-, and hence on the color of the solution. So if we're going to redraw this equation here, we're going to interpret it very similarly to how we interpreted the heat in the equation. Because if we have added HCl, we don't exactly have HCl in our equation over here, but we do have H+ ions. And if we link this to our acids and bases section, HCl over here will break off and form H+ ions and Cl- ions. So if we're increasing HCl over here, we're increasing this side of the equation, our reactants. And what happens if we're increasing our reactant side? Just like the seesaw analogy earlier, we are pushing up the seesaw. There's a ball over here, and therefore it's going to favor the forward reaction rolling down the seesaw in order to balance this equation, which means they were referencing how the dichromate ions over here, how they'd be affected, and therefore they would increase as the forward reaction is being favored. We have more reactants over here, which would collide with these reactants over there, forming more products over here, and also more water as a byproduct as well. So they said over here, write only increase, decrease, or remain the same. Explain the answer for 3 marks. And we would say increase because increasing the HCl concentration will result in an increase in H+ ion concentration as well. This will in turn favor the forward reaction. And then heading back to the question, they said, hence on the color of the solution, if we're favoring the forward reaction over here, we're going to turn the solution more orange. Therefore, we say more dichromate ions makes the solution more orange. And writing increase, as well as these 2 points over here, and this point over here would earn us 3 marks over here. And we've just covered heat as well as concentration for chemical equilibrium. The only other thing that can affect chemical equilibrium is pressure when it's coming to gases over here, but they aren't asking any pressure questions in this section, which means we've dealt with the Le Chatelier portion, and that'll lead us to the Rice table portion in the next part. The questions are always split like this, because 6.2 over here says consider the following chemical reaction. We have 2CO gas, which is very important. Gases are the only things we take note of when we're dealing with Kc, and we have CO2 gas over here, also important, and then a C with a solid. If ever we need to work with a solid and there's only a solid on one side of the equation, we would just treat that as 1 in our Kc. But if there is a gas on the same side as it, we just ignore the solid when it comes to Kc. So here they've given us the Kc value of 10 at 1095 Kelvin. And then they say a 1,0 decimeter cubed sealed vessel at a temperature of 1095 Kelvin, as they mentioned over here, contains CO and CO2 gas. An excess of solid carbon, as we mentioned, is formed. The concentration of CO is 1,10 times 10 to the negative 2 mole.dm to the negative 3, and the concentration of CO2 is 1,21 times 10 to the negative 3 mole.dm to the negative 3. So they gave us the concentrations of both of the gases, and then 6.2.1 says, is the system at equilibrium? Support the answer with a calculation. So one thing we know is that Kc is the concentration coefficient when the gases inside a beaker are at equilibrium. So if we are trying to prove this, what we can do is we can take their concentrations and see if it does in fact equal 10 over here. Because if it equals 10, then it means it's reached equilibrium again, that the forward and the reverse reaction are at the same rate, which means that we can go Kc over here. We can make that equal the concentration of CO2, square brackets. There's a 1 in front of the CO2, which just means our exponent over here is to the power of 1, which means we don't have to write it. But when we come to the concentration of CO, we see that there is in fact a 2 over there. So we have to put it to the power of 2. A reminder that Kc is our concentration of our products over the concentration of the reactants. And that's why we put the CO2 first, because that is our product over here, and the CO to the power of 2 in our denominator, because that is our reactant. Which means if we're dealing with the concentrations that they have given us, we can go ahead and write the concentration of CO2, which was 1,21 times 10 to the negative 3, and we can put that over 1,10 times 10 to the negative 2. And then we just have to go ahead and square this one like we had over here. So if we plug this in our calculator, we'll see that we do in fact get 10. And then heading back to the question, them asking is the system at equilibrium, we'll then say Kc value is the same, i.e. it was 10 before this reaction took place, and then it's 10 now. So Kc value is the same, and therefore system is in equilibrium. And this over here would earn us 3 marks over there. And then last question, 6.2.2 over here for 7 marks, says carbon dioxide gas is added to the system and the mixture reaches a new equilibrium. The equilibrium concentrations of CO gas and CO2 gas are now equal. Very important for us. The temperature remains constant at 1095 Kelvin. Very important that the temperature remains constant, as temperature is the only thing that affects Kc, which means that we'll have 10 as the Kc value before and then also 10 as the Kc value now in this new reaction. So it says calculate the amount in mole of carbon dioxide that was added to the system. So I'm just going to go ahead and rewrite this for us. So we have our reaction. Our solid isn't important for what we're about to do, because we are about to do a rice table with the gases. So a rice table is something like this, where we have R, I, C, E, and then we have C again, which is our concentration. So R means the ratio, I means the initial amount of moles, C is the change in moles, E is the equilibrium in terms of moles, then as we mentioned here, C is our concentration, which is no longer in moles. So the whole first portion over here has to do with moles. And what we're dealing with is our 2CO over here, the one gas on our reactant side, and the CO2 over here, the other gas on our product side. So the ratio is the number in front of both of these, which means the number in front of CO is a 2 over here, and a number in front of CO2, our mole number, is 1 over here. In order to calculate our initial moles, what we have to do is look at the concentration that they had previously before this new reaction took place, because this is the second second reaction we're doing, we are now using the previous equilibrium value as our initial values over here. But they didn't give us the moles of them in equilibrium, they did give us the concentration. But that is quite easy to calculate in this scenario, because for our CO over here, they told us that our CO's amount of concentration, if we go C equals N over V, the C value is 1,10 times 10 to the negative 2. And then they also said up top here is that we have a 1,0 decimeter cubed volume. So that is a 1 over there. And then our N over here is what we're looking for to plug in to our initial moles over there, which means that anything multiplied by 1 is just the same thing, which means our moles are just 1,10 times 10 to the negative 2 for the initial moles now of this new reaction. Because this was at equilibrium, now we're taking this and this is our new initial moles. So we can just go ahead and write that 1,10 times 10 to the negative 2. So we got the initial moles of our CO gas over here, but we can't just go ahead and do the same thing for the initial moles of our CO2, because this question is saying that carbon dioxide gas is added to the system and the mixture reaches a new equilibrium. So we don't actually know the initial moles over here. It technically would be 1,21 times 10 to the negative 3 as we have over there, plus Y, because we don't know how much mole was added to it. So we can do it like that, but one thing that might be a bit easier for us to deal with is that they are now equal and the temperature remains constant, which means that if we're going to go into our KC formula where we have the concentration of our products over the concentration of our reactants, a reminder that these are just gases here. So our product is CO2 to the power of 1 and our reactant is CO to the power of 2 because of the molar number in front of it. If they're telling us that Kc is the same, therefore we have a 10 over here, and then we're going to have to do an algebraic equation, because a reminder that the concentrations are equal, which means that they are exactly the same, and what we'd usually plug in to this formula here is the concentration. So it means if the concentrations are equal, we can just call them x, and then we can start to solve for this, because at the top we have x to the power of 1, and at the bottom we have x to the power of 2 based on the molar number in front of it. If we go ahead and simplify this guy is going to go, the 2 is going to disappear as we simplify one of the x's over here, and then if we're going to resolve this where we have a 1 left at the top, we're going to bring the 10 down to the bottom, and we're going to move the x up top over there. So we're just cross multiplying now, and this is telling us that the x value is 0,1 mole.dm to the negative 3. And that is just because the temperature remains constant, therefore Kc is the same, and they are now equal in terms of concentration, which means this guy is x and this guy is x as well. So when we sub them in the equation, we can just go ahead, plug them in, have the correct exponents based on their molar numbers, and then solve for the actual value of x. So we have 0,1 over here and 0,1 over here. And if we're then going to unwrap this, we have C equals N over V, like we have in the little formula over here, where if we bring it down here, our volume is over 1, and therefore our concentration is 0,1, and our N is over there. Anything multiplied by 1 is the same thing, and therefore our equilibrium mole amount is also 0,1, just because volume is 1, and therefore that won't change the values between the concentration and the equilibrium mole. And this puts us in a really good position, because as soon as we have values over here, we can calculate the change in moles. And this is very good for us, because if carbon dioxide gas was added to the system, it means the reverse reaction will be favored, which means that we are going to gain CO. There will be more CO at equilibrium than initially, which means if we just take 0,1 minus 1,10 times 10 to the negative 2, we have added 0,089 moles to the CO at equilibrium, which means that if this guy is adding, this guy is subtracting on this side, as we have favored the reverse reaction. And as we mentioned, the change in moles is very important, because here we can do a molar ratio. By that, if this guy is 2 and this guy is 1 over here, we can divide the 0,089 by 2 and we'll get 0,0445 over here. The change in moles is the only place that we can use our molar ratios to figure out how much things changed by in relation to one another, which means that once again we can go 0,1 minus 0,0445, and we can figure out what our initial moles is on this side, which was the objective this whole time, which means we have 1,445 times 10 to the negative 1 over here, and that would have earned us 5 marks so far. And then the last step in the chain is calculate the amount in mole. As we have here, we have the initial moles of carbon dioxide that was added to the system, and what we can do is we can go N added, the amount of moles added equals the amount of moles for the new initial minus the amount of mole at the previous equilibrium, because they didn't just take this amount of concentration or mole and put it over here. They added more CO2 to the mixture, and therefore we had to calculate the new initial and compare it to this previous initial. So therefore our new initial is 1,445 times 10 to the negative 1, and we're going to subtract the answer we have over here, the 1,21 times 10 to the negative 3, and that will equal 0,143 mole over there. And these would earn us our last 2 marks, because then we calculated the amount in mole of carbon dioxide that was added to the system, and that would earn us 7 marks over here and 18 marks for this whole section. Question 7 over here, so this is an acids and bases question. So 7.1 says the pH of a solution X is measured before and after adding 10 drops of concentrated sodium hydroxide solution NaOH to it. So we've added 10 drops of concentrated NaOH. We have our initial pH over here, as we can see, and our final pH over there of 12, as we can see as well. So initially it's 7, nice and neutral, and then final pH is 12. So a reminder of the pH scale, we have a 1 to 14 over here. 7 is neutral, 1 would be acidic, and 14 would be basic. NaOH is something basic because we have our OH over there. When we have OHs, we have OH minuses, and these are our hydroxides that make us more basic. Okay, so then 7.1.1 says what is meant by a concentrated NaOH solution. And this is just a sort of definition question talking about concentrated versus not concentrated. As we established, NaOH is a base, which means concentrated means we have a high amount of OH minus hydroxide ions when dissociated in water, or when compared to the amount of water particles. Okay, so this would earn us 1 mark over here, saying that a high amount, so a high concentration of OH minus hydroxide ions, which are what break off from a base, we form these hydroxides over there when dissociated or when added to water. And then 7.1.2 says what happens to the concentration of the hydronium ions, so not the hydroxide ions like we have over here, in solution X, right? Only increases, decreases, or remains the same. Explain the answer in terms of the ionization constant of water, Kw. So if we look here on our formula sheet, we have our Kw constant, where it is the concentration of H3O plus multiplied by the concentration of OH minus ions, and that equals 1 times 10 to the negative 14 at 298 Kelvin, which is 25 degrees Celsius. So this is just room temperature over here, but what this means is that we have to use this 1 times 10 to the negative 14 in our answer, because if we set up this equation over here, we have the concentration of H3O plus ions multiplied by the concentration of OH minus ions, and that equals 1 times 10 to the negative 14. And what happens is that the Kw value of water remains constant. Okay, so if we have increased the amount of OH minus ions, and these two things are multiplying, the concentration of H3O plus and OH minus, if we have increased the OH minus ions, therefore the H3O plus has to decrease in order for this to remain the same. Okay, so therefore we can just go ahead and write decreases. And to explain our answer, we're going to mention exactly what we just said, that since the hydroxide ions, the OH minus ions, increase, the H3O plus ions will decrease because Kw stays constant. Cool. And that would earn us 3 marks over there. And then 7.1.3, a follow-on question. We're going to see how we can use 7.1.2 in 7.1.3. It says calculate the concentration of the OH minus ions in the final solution. So we have our final solution over here of 12 for the pH. So if we reference our formulas, we first have to get our pH, which equals negative log square brackets H3O plus, which represents the concentration of the H3O plus, and then we can go ahead and plug that into our Kw formula to get the concentration of our OH minus ions. So we can go ahead, we can write pH equals negative log H3O plus. Then they want the final pH, so we plug in our 12 over there. Negative log is still here, and the square brackets of H3O plus, we could just write X over there. It's just important that we know that this is our concentration. So what we're going to have to do is we're going to have to unwrap a log because we cannot divide by log. So in a section, when there isn't a base on a log, it means that we have base 10. And one thing I like to do for logs is write 3 squared equals 9 because that statement is true. And what we have to do is we have to drop the base. So the base is this 3 over here. We add the log, we then drop the base over there, and then the 2 and the 9 are going to swap, which means that the 9 will go over here, and this will equal 2 over there. The exponent becomes the subject of the equation, which means that we already have a log, so we have to unwrap our log working backwards, which means that we first have to take our negative over. We have a minus 12 over here, then we're left with log base 10, square brackets H30 plus, and then what we have to do, like we drop the base over here, we're going to move the base up to be the subject over there, and in turn dropping the log that way, and then what we have to do is this guy is our exponent. As we saw here, the 2 was the exponent moving back to the base, which means we have 10 to the negative 12 over here, and then we're just going to take the concentration of H30 plus to the other side by itself, which is ultimately the aim for us to get the H30 plus by itself. So if we are having any difficulty trying to remember that the reason we're doing this is to get H30 plus by itself, so therefore it will have to be on one side of the equal sign by itself. What we can then do is rewrite our Kw formula. So we have Kw equals 1 times 10 to the negative 14, and that equals the concentration of H30 plus multiplied by the concentration of OH minus, which makes this quite easy for us because now we can just go ahead and sub this guy into there. So we have 1 times 10 to the negative 14. This will equal 10 to the negative 12 multiplied by what we want, which is the OH minus ions, which means that we can just divide this by 10 to the negative 12 over here, divide this by 10 to the negative 12, and the answer for the concentration of the OH minus ions is 1 times 10 to the negative 2 mole dot dm to the negative 3. Okay, and that would earn us 4 marks over there, calculating the concentration of the H30 plus hydronium ions, and then subbing that into our Kw formula to get our concentration for the OH minus ions over there. And then 7.2 over here says a learner titrates, very important, a sodium hydroxide solution with a standard hydrochloric acid solution with a concentration of 0.0958 mole.dm to the negative 3. Okay, so we have our equation here, our sodium hydroxide and our HCl that are being titrated, and then we'll form our precipitate over here and water. Water is almost always formed because we have our OH minus ions over here from the sodium hydroxide, our base, and the H30 plus ions that break off from our acid over here, our HCl. And when these guys collide with each other, OH minuses and H30 pluses, acids are proton donors, so therefore this guy over here donates a proton to this guy, a proton being the H plus ion, and therefore OH minus getting another H plus turns it back into water, and H30 plus having given away another H turns it into water, and therefore these guys neutralize each other. So what's important is how much is left, because sometimes we run out of H30 pluses first, and therefore there'll be OH minuses left because they cannot neutralize to form water again. Okay, that is just something to note when it comes to questions worth more marks, because then we're usually using pH and trying to see what is left in the beaker. But for now, the products are less important. The reactants are what we're going to be working with, because those two guys ultimately titrate. Okay, so it says the learner uses a pipette to transfer 20 centimeters cubed of this sodium hydroxide solution into a conical flask. Okay, so we have something like this, and adds 2 drops of indicator. The solution is then titrated. Ultimately, they balance each other exactly, which means we don't have anything in excess, like we were chatting about, no OH minus ions or H30 plus ions that are in excess. With the hydrochloric acid until the end point, the moment where they're exactly balanced, is reached. The titration is repeated 3 times. A table of the learner's results is as follows: titration number 1, 2, 3, and volume of HCl added in centimeters cubed, something to keep in mind because we'll usually want decimeters cubed, and we have 20,05, 20,15, and 20,10. So then 7.2.1, to help us with the next question, says calculate the average volume of the hydrochloric acid. So we have our volume over here. If we want the average, we're going to take all 3 of them, add them up, and divide them by the total amount of trials or number of titrations, and that is 3, because we have 1 trial, 2 trials, 3 trials over here. Okay, and this will give us 20,10 centimeters cubed. And if we want to, we can convert it to decimeters cubed, and we divide that by 1,000. So therefore we have 0,0201 decimeters cubed. The reason we divide this by 1,000 is because deci is 10 times bigger than centimeters cubed, but because they are cubed units, it's dividing by 10 cubed, and therefore 10 cubed is 1,000. Cool. And that would earn us 1 mark over there. And then 7.2.2 says, prove with a calculation that the initial concentration of the sodium hydroxide solution was 0,0963 moles.dm to the -3. Okay, so this is a 4-mark question, and they have used the word titrated a lot of times, which means that we can go ahead and look at our titration formula up here, because this is a very nice formula to help us, where we have our concentration of our acid multiplied by the volume of our acid over the concentration of our base multiplied by the volume of the base, and that equals the mole of the acid over the mole of the base. We'll see why this formula is very nice, but let's go ahead and write that, and we can see what we can sub in to the formula, because we have Ca multiplied by Va over Cb multiplied by Vb equals Na over Nb. So we're trying to calculate the initial concentration of the sodium hydroxide, our base, okay? Which means that our Cb is what we do not know. So that means we do know the volume of the base. So let's go ahead and look for it. As we can see here, the learner uses a pipette to transfer 20 centimeters cubed of the sodium hydroxide solution. So we have a 20 over here. One thing that's nice for this formula is that we can keep it in centimeters cubed, because we have centimeters cubed over centimeters cubed, and ultimately we don't have to convert them to decimeters cubed because they will take care of themselves. So we can't go wrong if we do convert it to decimeters cubed, but for this one we can keep it in centimeters cubed. Okay, which means that the concentration of the acid we have to know, because they told us at the top over here, with a standard hydrochloric acid solution with a concentration of 0,0958. So we can go ahead and write that over here, 0,0958, and then what we can do is we calculated the average volume of hydrochloric acid in 7.2.1. So the average volume, like we had over here, was 20,10 centimeters cubed. We just have to put it in centimeters cubed, as we put centimeters cubed at the bottom. Okay, if we had converted this guy to decimeters cubed, we'd then also sub in the decimeters cubed volume over there for the acid. And the other cool thing about this formula is that for the mole amount, we can just take the numbers in front of these guys. So we have a 1 over there and a 1 over there, which means we don't actually have to calculate the amount of moles. We can just use their molar numbers that are in front of the reactants over there. So therefore, in front of our HCl, we have a 1, and in front of our NaOH, we also have a 1 over there, which means we can just go ahead and solve for this by getting Cb up at the top by itself, which means we have Cb over there. 1 over 1 is just 1, so that is good for us. Then we have 0,0958 multiplied by 20,10 over 20 over there, which means that if we type this all in our calculator, the concentration of the base is in fact 0,0963 mole.dm to the -3, like they were asking us to prove over here. So prove with a calculation that the initial concentration of the sodium hydroxide solution was in fact this. Okay, so this would earn us 4 marks over here, and if we didn't calculate this value over here, we would then just use this answer in our next question, because 7.2.3 down there is a follow-on question that requires us to use this amount. Okay, because they say the standard sodium hydroxide solution is used, the one that we just calculated, to determine the percentage by mass of phosphoric acid H3O+ in a commercial brand of rust remover. Okay, we have a 10-gram sample of the rust remover is weighed off and transferred to a volumetric flask. Thereafter, the flask is filled with distilled water up to 250 centimeters cubed. Then 10 centimeters cubed of this diluted solution of the rust remover is titrated with 24,45 centimeters cubed of the sodium hydroxide solution. Okay, the balanced chemical reaction is as follows. We have 3 NaOH plus H3O+, and then we have our products over here, which are usually unimportant for us, especially for big mark questions like the 7-mark question over here. So the balanced chemical reaction is as follows. We're going to focus on the reactants over there. And then 7.2.3 for 7 marks says calculate the percentage by mass of phosphoric acid in the original undiluted rust remover. So one thing also to note that there's a titration over here. We titrated it on the last step, and it's very important to see how we can move backwards in these types of questions, which means I'm going to go ahead and rewrite this formula for us. So we have 3 NaOH plus H3 H3PO4, and that goes to Na3PO4 plus 3H2O. And what is important are our reactants over here, which means that if we have them in two separate flasks, I'm just going to do this for now. This flask over here is our 3NaOH, and we calculated its initial concentration in the previous question. So we had initially 0,0963 over there. Then here we have our H3PO4, and they said a 10-gram sample of rust remover is weighed. So we have a mass over here, and it is 10 grams over there. And they transferred it to a volumetric flask. Thereafter, the flask is filled with distilled water up to 250 centimeters cubed. Okay, so we've added it here. There's a volume of 250 centimeters cubed of water specifically. Okay, so this would be our H2O. So we are diluting it, and then we're going to move down here just now. But before that, we also had our volume of NaOH that we calculated earlier, and that was 20 centimeters cubed, or 0,02 decimeters cubed. Okay, we're just getting all the information down, because then they're adding these two guys together. They said 10 centimeters cubed of the diluted solution of the rust remover. So they only took a little beaker out of here to scoop up some of the volume. So it wasn't all 250 centimeters cubed. It was only 10 centimeters cubed over here that they were pouring into this mixture. The rust remover is titrated, meaning that it's balanced. There are no OH minuses or H3O pluses left over. These guys have neutralized to just form the water that we have over there as our product. Okay, so this is not a pH reaction, because pH is only looking at what is left over in terms of hydroxides and hydroniums, and it is titrated with 24,45 centimeters cubed of the sodium hydroxide solution, which means that scrap this initial one. They've given us the volume that titrates. We have 24,45 centimeters cubed over here. Cool. And these guys titrate and are therefore balanced. So then it's saying, as we mentioned, calculate the percentage by mass of phosphoric acid in the original undiluted rust remover. So they're looking for percentage purity of the mass over here, because it isn't just 10 grams over there. That would be the whole impure substance, which means we just want to know how much of the 10 grams is the H3PO4 over there, which means we've gotten all this information down. I just like to start like this to see what information we have in which beaker. It just helps me see if we're going forward to see what's left over here, or if we're working backwards in this case to figure out how much purity of the H3PO4 plus we had in our rust remover sample. Okay, because that is an impure mixture over there. So if we're looking in all three beakers over here, this guy is unknown. This is where we're ending off. So for 7 marks, we will not start with the H3PO4. Okay, we also don't have enough information of the mixture in the beaker over there, which means we are going to start with this information here, because what we can do, if we have a C and a V over here, we can get the moles. Getting the moles is very important for us, because C equals N over V. The concentration, like we calculated over here again in 7.2.2, is 0,0963 over there. The moles is what we want, and they told us the volume by which it titrated, by which it is exactly balanced. So we can go ahead and write 24,45, but something to watch out for is that we can't do centimeters cubed over here. This has been given to us in centimeters cubed, which means we have to multiply it by 10 to the negative 3 in order to get it in decimeters cubed, which is what is required in this formula. So therefore, if we take this guy up and we multiply it, we'll get our moles by itself, and we'll get an answer of 2,354 times 10 to the negative 3, because at this stage we have calculated the amount of moles that was used in total from the NaOH over here, and if it is titrated, it is exactly balanced, which means the next step we can do is doing a molar ratio between the 3 over here and the 1 in front of our H3PO4, because we have our 3NaOH, and this would be our 1H3PO4. So we have a 3-to-1 ratio, and we just calculated the moles here for the NaOH. So we have 2,354 times 10 to the negative 3 over there, and then we have to divide it by 3 in order to get the amount of moles for H3PO4. So dividing this by 3, and therefore we'll have 7,848 times by 10 to the negative 4. and this is the amount of moles here. A reminder is that we're starting at the end, which means we had enough information to calculate in this first beaker here, but we are titrating them, which meant that they're all being poured into the same beaker here and then balanced, which means that if we're trying to see the location, it was balanced over here. This was the 3 NaOH that we actually poured into this beaker, even though we had all the information up here in that beaker by itself. And then, considering we've just done our molar ratio, we do not have the amount of moles over here inside this beaker. Remember, we scooped out some of the liquid over here, some of it with this little flask over here that is 10 centimeters cubed that we then poured into this mixture with our H3PO4. So location wise, we are in our little Erlenmeyer flask over here where we have 10 centimeters cubed. Okay, so then what we can do is that if we were in this location and we want to get back to this original beaker, because that is where our impure sample size is, we can just take this value of the moles that we have, 7,848 times 10 to the negative 4, and we can upscale it. By that, we multiply it by the volume that we want, because we want the 250 centimeters cubed over where we came from, which is the 10 centimeters cubed over there, which means we're just upscaling it by doing a ratio of our volume that we want over the volume that we have. And ultimately, the amount of moles in a bigger beaker, like this guy, will be more than the little beaker over here, okay? Or the amount of volume that we scooped up inside this little beaker compared to the amount of liquid that we have here in this bigger beaker, which means if we just type this in our calculator, we'll have 0,01962 moles over there. Okay, which means we now are inside this beaker over here where we have our volume of 250 centimeters cubed and our impure mass sample size of 10 grams. And we know that if this whole thing reacted and we had this impure sample size like a bath bomb, we have all these flowers and stuff inside of here, and then we react this bath bomb in water, only the bath bomb portion is going to fizz and we're going to be left with the unreacted stuff, which means that if we just came from what reacted over here, we know how much H3PO4 mole actually reacted in this reaction. Okay, so not all the stuff that didn't react, but this stuff actually reacted to balance the NaOH and the H3PO4 inside our combined beaker over here, which means that we don't have the moles of the whole impure sample size, we just have the moles of the H3PO4. And if we want the percentage purity by mass of phosphoric acid, we are now at a good stage because we can go N equals M over capital M to get our amount of mass of H3PO4, because we have the moles over here, 0,01962. We want the mass, and the molar mass we can get on our periodic table, because the molar mass for H is 1 times 3 over there, plus phosphorus. Phosphorus is 31 over here, and then oxygen is 16 over here for the approximate relative atomic mass. So as we were here, 1 times 3 is the amount of hydrogens times by their atomic mass. We only have 1 phosphorus, so we go plus 31 over there, and then there are 4 oxygens at 16 grams per mole per oxygen, so we go 16 times 4 over there. And that means we have a molar mass of 98 over here. We're going to then multiply it up top, going 98, multiplied by 0,01962, and this will give us the mass of the H3PO4. And if we put that in our calculator, we'll get 1,92276. Okay, so that means we have the exact mass from this 10 gram sample that was actually H3PO4 that did react, which means that the last step in the chain is to calculate the percentage purity by mass of phosphoric acid in the original undiluted rust remover, and all we have to do is write percentage purity equals 1,92276 divided by the impure sample size, which as we mentioned was 10 grams over there, and then multiply that by 100. And if we go ahead and type this in our calculator, we'll get 19,23% over there. That is the percentage purity of the phosphoric acid in the original undiluted rust remover. Cool. So to retrace our steps, we calculated the amount of NaOH because we had the concentration and the volume. It was then titrated, so we realized we could do a ratio to get from 3 NaOH to H3PO4, the amount that actually reacted. From there, we realized that, okay, we were inside our little Erlenmeyer flask over here with only 10 centimeters cubed, so we had to upscale our volumes to get 250 over 10 multiplied by the moles we have, because there'll therefore be more particles inside this big beaker over there, top right. And then once we're there, we have the exact amount of moles of the H3PO4 that actually reacted from our impure sample size. So we could then go ahead, calculate its actual mass over here, because we could get its molar mass from the periodic table, multiply that by the moles that we have to get the mass, and then last step was to put the actual mass that reacted over the impure sample size of 10, multiply that by 100, and we got 19.23% as far as the percentage purity over there. Okay, and that would earn us 7 marks for this question and 20 marks for this whole section. Question 8, where we're going to work through galvanic cells over here. So it says, a learner was asked to build a functioning galvanic cell. The following are provided. So we have a magnesium rod, a copper rod, a 1 mol.dm to the -3 sodium carbonate solution, a 1 mol.dm to the -3 magnesium sulfate solution, and a 1 mol.dm to the -3 copper 2 sulfate solution. Okay, so we're going to have to build this. They've given us the components. All of them have a standard concentration of 1 mol.dm to the -3. And then what we have over here, it says a partially labeled galvanic cell built by the learner is shown below. So we have 1, our electrode, 2, the other electrode. We have our salt bridge over here. The key that it's galvanic is a salt bridge and that they're in 2 beakers. Then we have 3, the ions that are in this beaker, and 4, the ion or electrolyte solution that is in this beaker. Okay, so 8.1 over here says if the electrons move from the left electrode over here to the right electrode over here, label the parts 1 to 4 using the information provided. Okay, so if we have electron flow over here in the external circuit, it means that this is our anode and this is our cathode. Our anode in a galvanic cell is negative and the cathode is positive, which is why the negatively charged electrons are moving towards the positive cathode in the external portion of our circuit. Okay, so a reminder that galvanic and electrolytic has to do with the movement of electrons, and we have oil rig. So this means oxidation is the loss of electrons and reduction is the gain of electrons. If we lose electrons, something negative, we become more positively charged. And if we gain something negative, we become more negatively charged. Okay, another memory device for this section is we have NOx. So we have NOx over here and we have red cat. So NOx tells us that oxidation occurs at the anode over here. And then this one tells us that reduction is taking place at the cathode, which means we know this is the cathode, and that means we're going to have reduction over here, and we know this is the anode, and therefore we're going to have oxidation over here. Okay, and as we mentioned, an anode is negatively charged in a galvanic cell, and a cathode is positively charged in a galvanic cell. Okay, another component of a galvanic cell is that it converts chemical energy into electrical energy. So we're going to put these chemicals in these 2 beakers and we're going to form electricity. If there was an ammeter over here or a voltmeter, we would see that electrons are flowing. We would get some sort of voltage and there would be current as well. These are just things to keep in mind as we build our cell and figure out which rod will be our anode, which rod will be our cathode, and then which solutions would work best based off of the rods. Okay, so if we're going to look here at our table 4b, we can then compare some things because we're looking for magnesium and copper specifically. Okay, so if we look for magnesium over here, we can see that we have magnesium over here, Mg2 plus 2E goes to Mg over there. Okay, and then if we're looking for copper, we're going to look for copper, but not with an ion on both sides, because this has a plus over here and this has a 2 plus over there. If we move down a little bit, we'll see that we have Cu2 plus 2E minus goes to Cu over there, which means we're looking for our Cu and our magnesium just because these are the 2 options we had here for the types of rods that we're dealing with. And then what we have on the side over here is that as we go down, we increase oxidizing ability. Oxidizing ability is backwards, which means it is the thing that is more likely to reduce. Okay, which means that if we only have the 2 options of magnesium and copper, and the thing that is lower down with a more positive electrovoltage over here is the thing that undergoes reduction. If we're going to reference our little note here that we have NOx and red cat, if we want the oxidation reaction at the anode, it means it'll be the thing that is more negatively charged. So as we move here, increase reducing ability, that means it is more likely to oxidize as we move higher up. So we have an ox over here, the anode oxidation occurs, and magnesium is higher up on our table 4b with a more negative voltage, which means that magnesium would work best as the negative anode over here, which means that if we have 1, 2, 3, and 4 over here, we now know that our anode, number 1, will be our magnesium rod. That means 2 over here, our cathode, will be our copper rod by elimination. And that means we've dealt with both of the electrodes. Now we just have to see which solution would work best with each of them. Because as we can see here, we have magnesium sulfate and copper 2 sulfate. Sodium carbonate is the odd man out because it doesn't have the same metal as the rod. Usually we would take the magnesium sulfate and put that in the solution with the magnesium electrode, okay? Because when we do, we put MgSO4. We put our MgSO4. These two guys break off, which means we get Mg2+ ions over there, and then SO4 2- spectator ions over there. So we put the whole MgSO4 in there, and these guys break off, and then we get the Mg2+ in that same beaker, which works very well for us, especially considering our reaction is Mg, and then it breaks off, and we have Mg2+ plus 2 electrons, okay? Which means we put the solution of magnesium sulfate in the same beaker where we have the magnesium rod over there. So that means number 3 here will be our magnesium sulfate. And that means last move would be to put the copper 2 sulfate in this solution here where we have our copper electrode over there for our cathode. Because then we put CuSO4 and same thing happens. We get Cu2+, that breaks off over there. We get the SO4 2-. Once again, just a spectator ion, doesn't get involved in our galvanic reaction. And then we'll have the electrons flowing in that circuit as well, which means we can just go ahead and write copper 2 sulfate over there. And that would build us the cell because we don't want to use the sodium carbonate as any of our electrolyte solutions. So there we go. So if the electrons moved from the left electrode to the right electrode, label the parts 1 to 4 using the information provided. That would earn us 4 marks over there. Because then 8.2 over here says write down the equation for the half reaction taking place at the cathode. So at the cathode over here, we have reduction taking place. Reduction is the gain of electrons, which means we're going to have our ion plus however many electrons we have, and this is going to form the metal that we're dealing with. Okay, which means we're gaining electrons. These electrons are floating in our reactant side over here, and then they're going to form as part of the metal over there on the product side, which means that we know at the cathode we had the copper. We're just going to have to reference table 4b in order to write this equation with the correct charges and the correct amount of electrons. Because as we go here, reduction is the gain of electrons, which means we're moving this way. Cu2+ plus 2e- goes to Cu over there, which means we can just go ahead and write that. Cu2+ plus 2e- goes to Cu. And if we wrote this with a double arrow, we would lose 1 mark, or if we wrote it with an arrow in the wrong direction, we would then get no marks over there. So if we write it like this, with reduction is the gain of electrons happening at the cathode, we have then got our ions and our electrons forming the metal on the right side. Okay, and that would earn us 2 marks over there, because then 8.3 says calculate the initial EMF of this cell under standard conditions. Because if we look over here, we have the formula for our cell under standard conditions on our formula sheet, which means we have the E cell over here, which is the E cathode minus E of anode. So we can just go ahead and write that along. So our electrovoltage of the cell equals the electrovoltage of the cathode minus the electrovoltage of the anode. And one thing to keep in mind is that considering the cell is all about converting chemical energy into electrical energy, we have to have a positive value here. If we didn't get a positive value, it means we switched up and made a mistake of which one is our cathode and which one is our anode. Okay, so that means the cathode, we know we're looking at the copper. So if we're going to reference our table, we can see that the charge of copper, Cu2+ plus 2e- goes to Cu, has an electrovoltage, like we can see here, of 0.34. So we can write 0.34 and then minus in brackets over here, because we're going to have a negative value for our magnesium, minus 2.36. So Mg2+ plus 2e goes to Mg, and we have negative 2.36. So minus 2.36. Okay, which means we have 2.7 volts over here. and we have a positive value because a negative and a negative makes a positive, which means that if we accidentally swap them, say now we had negative 2,36 minus positive 0,34, we would end up having a negative value, which means that, okay, this thing that we thought was the cathode is actually the anode, and this thing that we thought was the anode is actually the cathode. And it just means we have to swap them, and then we'd go back in the test and make any changes we needed to, like question 8.1, for example, when we built the cell that we had. Okay, which means that that would earn us 4 marks over there, which is quite nice. And then 8.4 says state one function of the salt bridge. Okay, so the salt bridge over here allows these ions to pass through. So this Mg2 plus and the Cu2 plus allows them to pass through both ways. So we have these ions passing through the salt bridge while the electrons flow in the external circuit from anode to cathode. Okay, which means that the salt bridge completes the circuit by maintaining electrical neutrality, because it provides a pathway for the ions to be exchanged. Okay, so that would earn us 1 mark over there, as we stated one function of the salt bridge. Okay, and then 8.5 says, how will the following changes affect the initial EMF, the E voltage that we had of 2,7 volts of the cell? So write only increase, decrease, or remain the same. 8.5.1 says the concentration of the Mg2 plus ions is increased. Okay, so if we go ahead and write down our Mg2 plus reaction over here, which takes place at the anode, and then oxidation occurs at the anode, which means we're losing electrons. It means we have Mg goes to Mg2 plus 2E minus, which means that in this beaker over here on the left over there, where our Mg2 plus is, they have increased the concentration of the Mg2 plus ions, and they're asking us how will this affect the electro voltage, the amount of initial volts that passes in the circuit. And considering we have oxidation, which is the loss of electrons over here, and we want to lose electrons so that the voltage can then increase, if we have increased the Mg2 plus, imagine this was a two-way arrow, it would slow down the oxidation process, because if we have increased the side, it would favor the reverse reaction. Or another way of putting it is that there would be less of a tendency for this Mg to break down into Mg2 plus and 2E minuses. Okay, so if we have increased the ions of a side, we have to see how that is affecting what we want from it. Because oxidation, we want it to break down, but if we have added more Mg2 plus, therefore it would slow down the oxidation process, and therefore this whole thing would just decrease. So we can just go ahead and write decrease over here, and that would earn us 2 marks over there. And then 8.5.2, last question says, the area of the copper rod is increased. Okay, so our copper rod is up here, top right electrode, and they have increased the area. So what was this size, they now made a lot bigger, like that, for example. And we have already written our equation for reduction, but this does not work the same way as increasing the ions, okay? Because our reduction is gain, which means we'd have Cu2 plus 2E minus ions. This would go to Cu, and if we have increased the area of the copper, we might think that we might have more of this, and therefore, if there's more of this, it will favor the reverse reaction, and it'll be less likely for reduction to take place in order to complete the circuit. But this doesn't work. That can only work if we're increasing or affecting the ions in some way. If we are just increasing the area of the copper rod, it just means that there'll be more area for the same amount of stuff to react. Doesn't mean it will react quicker or slower, and therefore it will not affect our voltage. Our voltage will not increase or will not decrease. It will stay the same. So therefore we can just go ahead and write remains the same, as increasing the area of the copper rod will not change the initial EMF. The only other thing that could change the initial EMF was if we went to our electronegativity, and instead of taking copper metal over here, we could take something like silver, for example, which is lower down, has a higher oxidizing ability, or is a greater reducing agent, and therefore has a greater positive charge of 0.80 instead of 0.34 over there. Okay, which means that that would be the only type of change we can make as far as the metal portion in order to affect the initial EMF. But actually just increasing the area of the copper rod does not change any of that. Okay, so that would earn us 1 mark over there and 14 marks for this whole section. Question 9, it is the last question where we're looking at electrolytic cells. So question 9 says, impure copper is refined using an electrolytic process as shown in the diagram below. Okay, so 9.1 says, define the term electrolyte. We'll break that down just now, but what we have first, based off of our galvanic cell from the previous question, is we have an ox and red cat. This still occurs in this section. By that, the anode undergoes oxidation. Oxidation is the loss of electrons, okay? And reduction happens at the cathode. Reduction is the gain of electrons, which means that if we're gaining electrons, we're going to be more negatively charged because we have more negative atoms. And if we are losing electrons, we're going to be more positively charged because we are losing more negative atoms. Okay, all of this is exactly the same as a galvanic cell. The only difference is that in a galvanic cell, our anode is negative, but in an electrolytic cell, it is positive because we have conventional current, which means that the cathode over here is usually positive, but in this scenario, it is negative. We'll break down what this means because the whole function of an electrolytic cell is to use electrical energy and convert it to chemical energy, okay? Which means that as we can see here, we have this external circuit over there, and we have our positive terminal here, which means we are flowing this way, flowing over here, and then going this way back into our negative terminal of the battery. That means we are using electrical energy to create chemical energy. By that, in this scenario, we'll be refining impure copper, and often we're usually using this to coat something over here. Say now there was a ring over here, and we were trying to coat it in gold or copper, then this reaction would take place, and we would flow over here, and solid copper would coat this ring over there. So all of that being said, it means that our conventional current tells us the direction that we're going in because we are using electricity to create chemical change, which means that if we're going to break down the cell over here, the anode is at the positive terminal in this scenario, which means we have a positive terminal of our battery over here, which means our anode is positive over here. And this means this is our negative cathode in this scenario. So we have cathode over here, we have anode over here, and this makes a lot of sense for us because the anode has to undergo oxidation. So we've got oxidation is loss here, which means we want to lose electrons here, and then reduction is going to take place, or the rig is going to take place at the cathode because we want to gain solid metal over here with the idea of coating it or taking the pure copper and attracting it to this electrode so that we can then take it out of this beaker and use it for whatever we need it for, which means we've now oriented ourselves in the circuit. And let's check what 9.1 is saying, because it says define the term electrolyte, okay? A 2-mark definition referring to the electrolyte, the solution inside of this beaker. And an electrolyte is a substance whose aqueous solution contains ions and can conduct electricity, which means we might have like Cu2 pluses inside of the solution in this aqueous solution. And because it's a Cu2 plus instead of just a normal Cu like this, therefore we have electrons in the beaker as well, and these electrons can conduct electricity. And that would earn us 2 marks over there for 9.1. And then 9.2 says name a suitable solution that can be used as an electrolyte in this process. Okay, so we just mentioned something about Cu2 plus, but we cannot just put Cu2 plus into the solution because we don't find Cu2 pluses in nature by themselves. By that, we always come from some sort of compound, and the compound that we're dealing with is CuSO4. Okay, we are going to have to name it, but SO4, like in the previous galvanic section, is a good spectator ion, okay? Which means that we have SO4 over here, it has a charge of 2 minus. We have Cu over here, it has a charge of 2 plus, and they come together to form CuSO4, okay? But what happens is that in a beaker, if we put this CuSO4 in there, it will break off and dissociate, forming the Cu2 pluses and the SO4 2 minuses, okay? Which means we then have what we want, the Cu2 pluses, especially in this scenario where we are refining impure copper, and then we'll have the Cu2 pluses inside of this beaker, which means name a suitable solution that can be used as an electrolyte. We can just go ahead and write copper 2 because it has a charge of 2 in order to be balanced, sulfate, that being the spectator ion that will then break off and not get involved in the reaction. And this would earn us 1 mark over here. And then 9.3 says write down the equation for the half reaction taking place at the anode. So here we have the anode, we have an ox, so oxidation still occurs at the anode, which means if we want Cu2 plus and we want to lose electrons, we are going to use this guy over here. Our Cu2 plus 2E minus goes to Cu over there. We just need to arrange it correctly because oxidation is the loss of electrons, which means that we're going to have Cu and then we need to lose electrons, so that's going to break off and form Cu2 plus over there as our ion and 2E minus over there as our electrons that we have lost. So this is just finding this on table 4b like we we just did and writing it with the correct orientation of losing our electrons on the right side. And we know this because oxidation happens at the anode just like it does in a galvanic cell, because we want to lose electrons and copper so that we can ultimately coat it on this metal rod over there. And if we drew arrows going both ways, that would lose a mark, and if we drew it with the arrow going the wrong way entirely, that would lose both marks, so therefore we just earned 2 marks over there. And then 9.4 here says a precious metal such as silver, so we have Ag over there, which is usually part of the impure anode, sinks to the bottom of the cell. Okay, so it's part of our impure anode and it sinks to the bottom of the cell. Explain this observation referring to the relative strength of the reducing agents. So right now it's saying, why does Ag sink instead of also actually being oxidized and reduced on the electrode over here? So why does it sink, and why does the Cu2 plus in fact get oxidized and reduced? So if we go ahead and look here and we compare our copper to our silver, we can see that copper over here is 0.34 and we have our silver over here as 0.80. And as we move down the table 4b, we have increasing oxidizing ability, which means it is more likely to reduce. But if we're moving up, it has an increased reducing ability or is more likely to oxidize. And what we're looking at is the fact that we have the Ag dropping down from our anode, and therefore it is not oxidizing. Our Cu2 plus is oxidizing because our Cu2 plus is higher up the table with a lower electrode voltage over here, and therefore it is more likely to undergo oxidation. So it is all about where it is located on table 4b and which one has a greater relative strength to act as the oxidizing agent of the two. Okay, so we write silver, or Ag, is weaker reducing agent than copper, and therefore silver, or Ag, will not be oxidized at the anode. Okay, and this would earn us 3 marks over here as we establish that Ag is lower down over here. It is a weaker reducing agent because reducing agents oxidize, and therefore the copper will be oxidized at the anode and the silver will not, and therefore it will float down to the bottom just like they mentioned in 9.4. And this used the relative strengths from table 4b to explain it in terms of reducing agent ability. Okay, and that would earn us 3 marks over there. And then last question for this paper, 9.5 over here says after 10 minutes 1.6 grams of pure copper is deposited on the electrode. Okay, so we have pure copper that is being deposited on our cathode over here. We have 1.6 grams of pure copper, so no ions and there's no silver mixture. It is just the copper that has been lost from this electrode or from our beaker that is then being coated on our cathode over here. Okay, calculate the number of electrons, okay, that flowed through the circuit while this mass of copper was deposited. So earlier we wrote down our half reaction taking place at the anode. We can rewrite that or write the version at the cathode because reduction is gain of electrons, which means we have Cu2 plus 2E minus, and that'll form our Cu over here. So with electrolytic cells, we will oxidize and reduce the same element because we are breaking off copper inside the mixture, and then we want to gain that copper on the other electrode on our cathode over here. So this will be our cathode, this will be our anode, and we are undergoing the same process. Oxidation is just happening at the one electrode and then reduction is happening at the other electrode. But what this means is that if we are going to do some sort of molar equation over here for this one, we have 1.6 grams of pure copper that was delivered on the cathode. We want the number of electrons over here. We don't know how many electrons we have over here, but we are in an equation where we can get to moles and then work with the moles in this equation to calculate the number of electrons that we need. So if we just go ahead and write N equals M over capital M over here, we have 1.6 grams is the amount that has been deposited, and we end up having 63.5 grams per mole of copper on our periodic table. We can just go ahead, plug this in our calculator, and we'll have 0.02519 moles over there. Okay, which is great for us because if we have the moles of the copper over here, we can do a molar ratio of 2 for our electrons to 1 over here for our copper that we actually deposited onto that electrode. And as we can see here, there's a 1 in front of our copper. So 1 represents 0.2519 moles, which means we just have to multiply it by 2 in order to get this one over here, which means that we have 0.05039 for the amount of moles of the electrons in this beaker, which means that we aren't very far from our last equation, because what we have on our formula sheet is the amount of electrons or the amount of atoms, because a formula that we don't use very often anymore is the moles equals the amount of atoms or particles over Avogadro's constant, okay, which is also on our formula sheet here, which means we can just go ahead and rewrite this formula where we have N equals capital N over NA, and if we're going to rearrange it, we want capital N by itself, so we have the moles multiplied by Avogadro's constant, and the moles that we just calculated was this one over here, the 0,05039 that we have for the amount of electrons after we did our molar ratio, and then Avogadro's constant on our formula sheet is 6,02 times 10 to the 23. And this is our final move, because here we're going to calculate the amount of particles or atoms, or in this case, the number of electrons that flowed through the circuit or the mass of copper was deposited, which means we have 3,034 times 10 to the 22, a large number because there were many electrons over there. And that would be our final answer over here for 9.5, earning us 5 marks for this question, 13 marks for this whole section, and 150 marks for this whole paper. Great job, guys. Let me know if there are any questions in the comments below, and then I will see you in the next video.